Why it's not just because it's a precipitation. It's not about how much precipitation falling down. It's about the precipitation and the wind direction and the slope. So by 3 vector, you can get the total precipitation falling in a single location.
And how much precipitation has fallen before?
Yes, and yes, how much and the quality of your soil, that is how much your precipitation falling before. So those information make the prediction is very hard, and therefore you really need to have local information with local people understand those things. In many places, at least I know in Taiwan, they simply have a threshold of precipitation. If it ran above this threshold, they just triggers a landslide warning. But it's probably not going to be too accurate, but it's better than nothing. But then there is a crying wolf situation in the end, but that's what they're doing.
So that's application for precipitation without talking about flooding.
Yeah, I think it's similar.
That's true. Yeah.
Yeah, but it's not. It's the landslides the answer.
It's not.
In California, there's often landslides, not from hurricanes, but yeah, I know like the National Weather Service has like very specific thresholds of rainfall in like an hour, depending on the terrain and whether if burned previously, because a lot of fire scars are very vulnerable to landslides, and so I don't know how they derive it, but they have very specific information about these mountains, like issue an evacuation because of the amount of rainfall expected in an hour.
But do they have those like a false alarm, very high false alarm rate? Do you know?
I don't know. I mean, I don't know what the probability of a landslide given their warning threshold is. Yeah, I know. I just know I've seen it in like warnings and weather forecast discussions about like for that, like these burn scars, we're gonna have a warning now because it's an inch and a half an hour.
Yeah, talk about burn scars. Maria Uriarte, who works at Columbia, she did a lot of study in Puerto Rico, looking at the impact of the winds in forests and trees. So we could talk about this kind of thing. So we're not talking about any ecological impacts or when you have a hurricane, the petrol industry. That will have a lot of environmental impacts. We have nothing of that kind of ecological impacts, environmental impacts, falling, that you can have. So I think that's missing there somehow.
Yeah. I mean, the other table would have been better to put that in. Yeah, the exposure part.
If we go back.
Yeah. Sure.
The exposure, oh yeah. So
Ecosystems.
yeah, so a few years ago, I did a paper with a whole lot of marine ecologists, and they were worried about the Great Barrier Reef essentially being damaged by mechanical wave action that just destroys coral. So yeah, they use synthetic tracks. They use Kerry's synthetic tracks to estimate essentially tropical cyclone waves in historical and future climate over different reefs. That was one example. Yep.
And I think the petrochemical industry in the Gulf of Mexico is a big one.
Okay. So should we talk about challenges, the outstanding challenges maybe?
Yes.
So sorry, go ahead.
Something before, those ecosystems include agricultural, does anybody look at that? I'm just thinking again, Hurricane Maria, Puerto Rico, yes, we talked about the landslides, the vegetation, but they depend a lot on local agriculture, and a lot of that was wiped out, and then for months, even years, they had both economical but societal issues.
These are economic damages and indirect ramifications of those, as we see that from the natural hazard perspective.
In this aspect, we can talk about multi-sectors. I mean, instead of just economical aspects, for example, agriculture can be a sector, economic sector. I will talk about multi-sectors. It can be interesting.
So if you want to lead the challenging part.
Sure.
Maybe the vulnerability side could be related to social vulnerability.
Oh yeah, that one.
Do you want to add that?
Yeah.
So we've got 10 minutes, but
And maybe
maybe
the indirect here, Jane. I would make it fall under yeah.
Well,
Yeah, you're right. You're right. Better like that.
so we've covered so we've covered data sets at the beginning, and we'll come up with this document that has different links, and we can hopefully share more or figure out where we're at as far as different data sets go. User needs we've kind of started touching on now in a broad sense, but I thought we could finish with the challenges. So where are we, what are the outstanding challenges in terms of, let's maybe stick to it could be all three, but maybe to keep it more guided, we could talk about the hazard, the outstanding challenges with modeling the hazard, or not.
I think
Want to go further?
one of the biggest challenges is the uncertainty we have, because if you want to project a future, then you need information from cement model, and there is uncertainty there. And ensemble mean doesn't necessarily give us the best answer as we hope. So that is some of the uncertainty can be continued reduced through improve our physical understanding of our science. Some just not. So especially for near-term projection where the internal variability is kind of important, then how to consider those is one thing we need to think. And another way is we believe in individual a risk model. Let's say if you do believe that there's individual model have their pros and cons. Even we release the data when you use, if I don't teach you how to use data, how to deal with the bias, then you probably would just think this is trash. Possible. It depends on which tier of data we provide. So those are the kind of.
I agree. I think there's still large uncertainty in the issues in the first column, project modeling. And we have large GCM, we have high resolution GCM, we have downscaling methods, statistical various methods.
RCMs.
We haven't really as machine learning methods. So we haven't really made a comprehensive comparison to understand
to quantify the
uncertainty and what that means, and which model has advantage and disadvantage and so on. So right now, people use these models more based on convenience. If they have connection with high resolution climate model, they use that. If they connection with chain, most people have connection with chain. I'm just kidding. So, but I did a comparison between our model with Carey Manu's model using the same rainfall model. If you use the synthetic tracks from Carey using synthetic tracks from us, you produce different results.
Yeah.
Not mentioning about climate models, various climate models produce different results. So I think there is a huge challenge.
Exactly.
So
and also the explicit tracks.
Promote that some years ago. You were involved in that, and we wanted to do a comparison with the industry, and we were very far in it, comparing the academic models with the private industry models, and we had some private industry, they were into it until one of the providers pulled out, and then all the private industry pulled out, and they wouldn't do it anymore. So I think it's important we could do a comparison of the academic models, but I think what's really driving what's happening in the world is a lot of the private, company models, and if we somehow could have a handle on that again, and try again to do that. That's, we tried and we failed, but I think it would be worth trying again because, our model is open source. Jonathan's model is open source, so people can use that. But then really Aon, all these other companies, they don't share what they're doing. That's really cool.
If I may reinforce a point, indeed. This part is more or less worked out. The uncertainties here are much more constrained. You can pick one flood model, one source model, or the other. They more or less do a very good job. They're very sensitive to the forcing, the resolution of the. So bring home this message. There are many things. Many tools that can be used. You can do everything on this side. the ball is in the field of the 3DC features.
Yeah.
That's the weird.
Well, I would say as well in exposure and vulnerability, because there are a lot of countries where there is not good information.
Yeah.
And as well, where in economical damage functions, we don't have sometimes enough data to represent the consequences. So
Yeah, you're right.
Exposure vulnerability campaign is big uncertainty too. It's just maybe for this group, that's more the big part. And future projection of the we have uncertainty on future projection of climate. We have a large uncertainty of future projection of vulnerability and exposure, where people are going to move and what are going to do to adapt to the climate. And there's also talking about this dynamic, like our decision will change our vulnerability exposure in the future, right? And then there's a feedback connection.
Can I say one last thing about the PC MAPE? Because I think it's the best time to call you for contribution to that comparison work. So Leo will take me to doing analysis. So we're going to to make sure we can get some very preliminary thoughts by Friday. If you can give us some access to the downscaling model, either Princeton or Chess, whatever, and then we can pose the data into this code, we turn it down and see whether can some better results. See.
I don't think it's clear yet what I think for asking people from data, we have to be clear exactly what data, what type of data we're talking about. Present climate, I think I'm with you, but I think you're a little ahead. Yeah. I think it has to be a discussion exactly what's going to be done and how, what's needed, what's variables, and what's the point.
Yeah, and so I think we're almost done here. So in terms of website, I'm thinking maybe I'll ask the climate school. They have been asking me to create some kind of research website, and I always ignore. Maybe
but that's a personal research website.
No,
that's what their blogs are getting.
Oh, but we can.
Put it on our Hugging Pass. Put it on Hugging Pass. Hugging Pass is like your machine learning open source website. You can host also the data and like a website.
But once we post it, can we continue maintain it? Like adding data if I have the right to continue maintain everything. But maybe you can send me a link. I can see.
Just share the Word document.
Yeah. Oh, that is fine.
Yeah, exactly.
And other people can join, and see how it goes before we need to use any formal other complicated. But I have another thought is about this climate audit. Yesterday we talked about the not real time, seasonal forecast. Is that possible to extend those models to seasonal forecasting? The insurance company probably talk more about seasonal forecasting.
They are talking about like 1 year, which is not really seasonal forecast. A lot of 1 year, 5 years. So seasonal forecast, it's that's not that. So it's different time scale.
Has any potential to be used for that?
Well, I think it has to be retrained a little bit. I mean, right now we have some kind of positive correlation with, let's say, with ENSO or with internal variability when I look at the correlation. And Johnson's model has much higher correlation, but that's mostly because how the seed is working. So, and I mean, it's possible to try, but I would say there's a potential, but not the current version of chess. I will have my doubts.
I think it's a new project.
Yeah,
you have to retrain it and redo it and see. I mean, the idea could work, but it's not just taking out of the shelf and use it.
Correct, but I'm just thinking this could be a opportunity or challenge or some direction, because if we talk about advantage of high resolution larger scale, high resolution climate models, some models could claim that they can do continuously projection or prediction and seasonal to decadal.
Yeah.
Well, for our model, risk model, we target at the long-term prediction, but
But I think it's something that you need funding. I don't think that's something you can do without funding. It's something that you need funding, you need people, you need.
Just quickly on that, Dongning, I think it's a great idea. And so I'm part of this lighthouse activity that's focused on annual to decadal timescale, so that's 1 to 10 years, which is quite hard. I agree, and I'll show on Thursday, I think there's some promise to use, in this case, I'm using Jonathan Lynn's model, but I think there is a way that we can use these models to try to understand predictability through the large scale, because it's forced by the large scale mostly on these timescales. So I think it's a good idea. Yep.
Yeah, so before we end, I'm shamelessly promoting our AGU session. This is on the climate-informed risk assessment extreme events. And it's not just about hurricane. And this will be the 3rd year, and our session is growing because I think there's a need in this society. And we are encouraging whoever, as long as you are considering assess the risk, whether you are using like a hazer or more impact sector, but just if you're using climate information to project, to inform the risk, then this is a session that very welcome. We have, so we have one invited speaker has confirmed will be Kerry. He will talk about, I don't know what he's going to talk about, but probably related to TC or reliability of risk
physical
models.
models for risk assessment.
Yeah, or his view on it. Yeah, so please consider and also encourage your colleagues who are doing wildfire or drought. Those are all pretty welcome. Yeah, thank you. Thanks, everyone.
Just a quick announcement, we'll have our machine learning lecture here in the cathedral, so we'll have a short break, but then we'll still be here, and then for the hands-on part, we'll go up in that conference room. So the first hour is general though, so if you want to just hear about machine learning without having to to code anything, the next hour is for you. If you want to hear both, you can stay here and then we'll go up.
So it's in here, right?
It's going to be right here, yeah, in like 5 minutes.
On your point, so
Then you can get coffee and just the number. Don't want people to start.
when I ran Jonathan's model,
He's leading the
simulated.
For the people on Zoom, I mean, I guess it's not that many.
Put ahead like another slide that has text, just to make sure. Yeah, these slides.
But it's just a transition is slow, right? And it's transition plus edge row.
Okay, yeah, looks good. Yeah.
Oh wait, I see the answer.
There are
Do you want me to be strict on time with you? Do you want me to
increase one size.
Keep an eye on time. 30 minutes, 3 minutes. Yeah, we'll start.
So I wonder, those are
differences in formation
hard by delay, stronger, and so
Paris
already are actually really
and
so if that were the case, like we had a large enough force to have a very
Well, you just
I might think about
sorry, question.
That's one of the maybe it's also they're not. So in reality,
you want me to ring the bell? So we're going to get started with a machine learning lecture. Professor Molina will be giving the first half of the tutorial. Then I'll take over. And then for those of you who want to try out, do we have a microphone? Thanks. I'm happy to shout, but Welcome everyone. So we will have a 1-hour machine learning tutorial. The theory is going to be here. And then for those of you who want to try, we have 2 interactive Google Colab notebooks, including data. And we will be doing exercises, so with the notebooks in 1 hour in the office upstairs. And so we'll have 30 minutes with Maria, and then I'll take over. Let's welcome Maria.
Do we want to unmute so that Zoom?
I think the cathedral is unmuted if I'm not.
Okay.
Where is the cathedral sound? You know? It's probably on the screen.
Yep. It's, yeah, okay. Okay, hello everybody. Thanks so much for your interest in machine learning. I'm hoping that we can give a brief overview, and I guess just to kind of get a feel for where we're all at, how many of us are already users of machine learning broadly?
How broad?
Like random forests, neural networks.
Depends on how you define. I have used cluster analysis for like 20 years. I never defined as machine learning.
Right. We are clustering, I guess. Yeah. All right. Well, we'll just go ahead and proceed and go from there. So we can. Yeah, so we do have a couple of learning outcomes that we're hoping that you all walk away here with. So the first one being understanding how to frame a machine learning problem. So for example, if you have a question that will be well suited for a clustering problem, we hope that you can leave here understanding that you would be using an unsupervised machine learning approach, and then understanding whether you should be doing a regression versus classification approach and so on. Yeah, so just being able to frame your ML problem as you are thinking about your specific application, and also understanding the importance of appropriate data pre-processing steps, meaning how to rescale your data, how you would do a train test split to ensure that you aren't leaking any of your training information into your evaluation of your model. And then also understanding how machine learning models are trained. We do have a couple of notebooks. Tom will be sharing several different algorithms. I will have an example with Emily on neural networks, so you can see how neural networks would be trained, and these would be very relatively simple models. And we're, of course, always happy to talk about more advanced methods if you're interested. And then Tom will give us an overview about the physics-guided machine learning models, and also understand the wide variety of different approaches that are available involving different types of physics constraints for your machine learning applications. So when we think about machine learning, as you just noticed, it is very broad, so it does entail quite a lot of different methods. And really, it can be anything ranging from k-means clustering to neural networks. And it's just the idea that we have an algorithm that we can give data to, and that it will go ahead and perform a task for us. So traditionally, on the left-hand side, if we think about expert modeling systems or expert decision systems, where I might understand from my domain expertise that a tropical cyclone typically has a certain pressure, typically has a certain maximum wind speed or minimum sustained wind speed to be classified a tropical cyclone. So I might set those thresholds from my own domain expertise. And the idea with machine learning is that we can try to move beyond that and have machine learning understand different characteristics of our data and identify what some of these variables and combinations thereof are important for the problem that we define. And feel free to ask a question anytime you'd like to interrupt. If we think about the different terms, we often hear AI and machine learning used interchangeably, but they do have distinct differences. The broader term is computer science when we're thinking about the entire field of studies of computers, so that also entails hardware. When we're thinking about AI, that does include machine learning and deep learning, but that also includes things like the theory of what intelligence is, right? So what do we even mean by intelligent machines? And then when we get to machine learning, we have our specific definition, which is this idea of having an algorithm or a computer that can essentially learn something without being explicitly programmed based on your domain expertise in our applications for the physical sciences. And then when we're thinking about deep learning, it's a subset of machine learning where we're specifically focusing on the use of neural networks for our different applications. I do think I showed this slide last week during my talk. The idea that machine learning has been around for a long time, since the 1950s. That's around the time that we had that definition established at a big AI conference. There was a lot of excitement, in fact, research with the perceptron algorithm, and then there was a lull in activity or excitement where we had our first AI winter, so reduced funding, reduced momentum, or maybe reduced hype. And then again, that excitement grew. We had backpropagation algorithm developed for the training of neural networks. And then again, another lull. And now we've been in a rapid upward trend with the excitement around neural networks. And I think a large part of that excitement stems from this competition called, from a data set called ImageNet. So in Stanford, there is Fei Li, I believe is her name. So she's a faculty there, and along with a number of other graduate students and team, they put together a very large, high quality data set called ImageNet. And that is a data set with a bunch of images of things like cats and dogs. And so people got together, classified or assigned labels for those images. This is a very, very large data set and enables competitions to take place where people could benchmark certain machine learning models and neural networks to see how well they could get them to perform this classification task with this very large data set. And so a couple of years into that, there was this very famous model called AlexNet. So this is a convolutional neural network that was deep, and it got a lot of attention because of how well it performed this classification task. And since then, we've had a number of additional advances. We've seen them now in the physical sciences with things like GraphCast, ForecastNet coming out of the private sector, along with advances in like causality, like Tom was sharing in his talk earlier today. And I think a lot of that has to do with a number of different advances. Some of that has to do with those large high quality labeled data sets. So ImageNet just being one, there's been many, many more that have come out since then. So there's been this push on this advancement of algorithms that can perform tasks really well with these data sets. We have GPUs now. Does anyone know how GPUs got developed? Like, what was their original purpose?
Gaming system.
Gaming system. So gamers wanted to have awesome graphics for their games. And it turns out that that actually is very good for neural networks and machine learning for matrix multiplication. So that's also helped AI. So it just happened by chance, I guess. And then I'll argue as well that a lot of advances have come out of the big push with open source software. So if we think about Python software, we have a very rich ecosystem of many different packages that can do all kinds of tasks. And that wasn't overnight, right? Python has actually been around for like more than 30 years. By the way, Python, the software is named after Monty Python, not after the snake. Oh, yeah. And so here's like a Stack Overflow trend plot that you can see over time how the number of questions asked about Python exceeds the number of questions asked involving any other computer language. So just illustrating how Many people are using Python and asking questions about it and interacting with each other on these online platforms. And many of the deep learning libraries like PyTorch, TensorFlow, and JAX have interface with Python or use Python to some extent. So yeah. When we're thinking about the use of machine learning, and I will specifically focus on neural networks, and neural networks can be very simple. They don't have to be these massive models. I like to think about splitting the workflow into 3 different steps, where we have the data pre-processing steps, and that can be very involved. Then we have the training the model step, and then we have the last step, which is where we can evaluate how well our model is performing. We can then also apply things like explainable AI to ask questions about why is it performing in that way, and a number of other tasks. And so we have a question for you. So we are wondering, for your specific machine learning project, how much time you might spend on preparing and transforming your data. So do you think that you would spend less than half the time, or more than half the time on the data pre-processing and transformation stage?
More.
So yeah, so it's more than half of the time. So we want to make sure we do spend some time here talking about the importance of your data. So if you put garbage into your neural network, just the same way that if you put garbage into a physics-based model, garbage in, garbage out, right? So you're not going to, you really need to make sure that you take time to understand your data and also address any potential limitations that may bias and mislead your neural network. And so last week as well, I also showed this slide highlighting that while I'm going to focus on neural network applications, there are quite a large range of different machine learning models, and they do span quite a big range in terms of how much data is needed. And when we're thinking about neural networks, especially big neural networks, that really requires having quite a lot of data, although there are, of course, methods like transfer learning and meta learning that can shift us from a data-rich domain into a space where we have less data available. And in the class that I teach, in fact, Emily just took that this spring, there is a long list of different methods for neural networks. We have neural networks that involve time series, such as recurrent neural networks, and that's an entire class of neural networks. There are convolutional neural networks that you can leverage spatial images for. And then there's unsupervised methods. So beyond clustering, you can do things with self-organizing maps and autoencoders. But that, of course, would entail not just an entire semester. I would even argue that maybe more than an entire semester for diving deep into, but just wanted to make you aware if you aren't aware yet. Otherwise, there's a couple of different categories that can help you start framing your problem. So the first one is, I would say, in the hierarchy of different decisions in your assessment of framing your problem. The first one would be whether you have labeled data. And that means whether, if I have a problem, do I know what the answer would be in a historical sense? For example, do I have 30 years of tropical cyclone data? And if I want to predict tropical cyclones, perhaps that can serve as my labeled data set. And in this case, this would be a supervised learning problem. So many of us are familiar with a very simple linear regression. So y equals mx plus b. If we know y and we have a number of y's, then we can use supervised learning. And then the other category would be unsupervised learning, where we don't really have a specific thing that we want to predict. We actually want to use machine learning to uncover patterns inside our data. And in this case, we could use unsupervised learning. And so this takes us into clustering, self-organizing maps, and autoencoders, and so on. And so in this case, if we go back to our example with our y equals mx plus b, where m is your slope, b is your intercept, or y-intercept in this case, and we would have no labels y. And I want to make you aware that there are a number of other ways that supervised learning and unsupervised learning come into play. There is semi-supervised learning and self-supervised learning. So these are just variations on these terms where maybe we have some labels in the case of semi-supervised, and then we actually want to perform a task where we learn from those few samples that we have and then continue training. And self-supervised could be that we have no labels and we end up learning some useful representation, and then that representation can serve as our label. In the case of classification, those could be, for example, our classes. And these are somewhat fuzzy depending on the application and who defined it in their paper and so on, but generally this is the definition that is being used, at least at the Department of Computer Science at the University of Maryland by my colleague.
So can you give a more specific example of how
yeah,
differ, like how?
So like I'll give an example with Gyron, a PhD student in my group. So he's doing weather regimes. And so he takes geopotential height, creates categories of weather regimes. So he uses unsupervised learning to create these clusters and then uses those clusters to predict them. So it's kind of like, sort of like self-supervised, but not really, yeah, I don't know. These are just more fuzzy definitions. Tom, do you have any thoughts on it?
Yeah, I think one is, imagine you were trying to label tropical cyclone on maps. But you with forecaster and they have a very subjective definition, so you can only do it with humans. So you would have forecasters sit and label maps. But then forecasters are expensive and impatient, so you can only label a couple of maps. And so then with the few maps that you have, you would train an algorithm to learn the rest. And that would be semi-supervised.
Yeah.
Yeah.
Great example. So there'd be like two different approaches. One, you ended up classifying the entire thing with unsupervised. The other one, it was too expensive to have people hand labeling. And just different ways to get around these issues with lack of labeled data. Something else that can help you determine what type of machine learning approach you're going to take, and one that's very important, is that of what your labels, in the case that you are doing supervised learning, what your labels look like. So for example, are you trying to predict a value in one location or in one grid cell of your map? Are you trying to predict an image, a region with a number of grid cells? Are you trying to predict something that has a time component and an evolution? That's going to start narrowing down what your focus should be on the type of machine learning that you're going to be using. And so here I list a couple of simple examples. If you're thinking about a single value prediction, that might be like a fully connected artificial neural network. If you're doing image-based, that would be a convolutional neural network. And if you have a time component, you may do something like a recurrent neural network being like an LSTM, transformer, and so on and so on. There's many different examples, and they don't have to be independent. You could have a LSTM convolutional neural network where you have a time component and a spatial component. Knowing that would be pretty important. Then there's our regression versus classification. So for regression, we have a value that we're trying to predict, and we generally have some sort of continuous range. Some examples of regression problems I went ahead and listed here. These are examples from our class. So here you can think about predicting the maximum wind for a tropical cyclone, and you know, whatever definition of your maximum wind speed is, your land surface temperature maximum in perhaps an urban area at a grid cell or even a spatial area. It could be a percentage of cloud cover over some domain. And you can even think about it in a bias correction setting. So you might be predicting how much to bias correct by. That would be a regression task. Go ahead.
Can you explain more on the bias correction?
Yeah, so for example, if I have a prediction system and that prediction system is going to predict temperature tomorrow, and I know that there's probably some systematic bias in that forecast, I can use machine learning to correct for that systematic error. So I can learn what that error typically is. Maybe it has some association with time of year, the location, whatever. And so machine learning can learn that relationship, and then I can give it that forecast, and it can bias correct it. It'll bias correct it by some value that it's predicting there's an error amount by, and correct in that way.
Right. Yep.
Yeah.
So sometimes the tropical intensity can also be a classification problem, right?
Yeah, we're not there yet. There is a TC example coming up, but yeah, that's right. And they're not totally independent. They can, yeah. So the next one is classification. So in this case, we would be predicting the class of something. So this would be some sort of discrete category. And in the case of a tropical cyclone, I don't have that example listed here. I thought I did from our class, but there, for example, if you're doing categorical prediction for a, like Saffir-Simpson scale prediction for a tropical cyclone, right? Like Dan said earlier, you know, he can give you a number of cats for your category. I love that joke. So yeah, so maybe the class that is going to predict is category 3 strength, right? So that would be classification. There's a number of other examples here. I mean, it doesn't have to be 5 categories. It could be binary, so it could be yes or no. You can ask, is that thunderstorm going to produce hail? Yes or no, right? So it can be a range of different class numbers and so on, and ways that you can do this classification task. In addition, you can think about like citizen science photographs. So NASA has this little program where they have people used to have to take photos of clouds. So you could think about like having a machine learning algorithm tell you what type of cloud is in that image. Right, so we can even move beyond our own physical science world where we have models or observations that in the like weather station sense into other types of data like photographs and text. All right, we have one more question here before we get going on some deeper topics. So here we are asking, if you had to prioritize only one of the following ways to make your machine learning model perform better, which one of those would have more impact? So would it be, all right, it's B. Yeah.
Yeah, you can say.
Oh, I say.
No, you can't.
Oh, I can't.
So what makes your machine learning model perform best isn't always the fanciest model, the fanciest algorithm, a bigger network, or a more clever loss function. Sometimes it's really simple, and it has to do with the quality and the size of your training data. Tom?
Oh,
Not showing up here.
oops. 30. We had 30, but you started late. I mean, we started late, so you have 5 to 10 minutes if we want to stand back.
That's good. Thank you. Yeah, so then if we think about the full workflow, right, so we're going to go ahead and first figure out what model we want to use and how we're going to solve this problem that we have. The next really important step is building our training data set and figuring out how we're going to clean up that data set before we proceed to train our model. And there's a couple of questions that I went ahead and listed here. These are questions that I ask students to think about, and I also made it for my own sanity. So there's a couple of things like how many variables are going to go into your neural network. The more variables you have, the more dimensionality you're adding to your problem. And then you can get into something called the curse of dimensionality, where you have too many variables and you need a much bigger data set to be able to capture some of these relationships. You can ask yourself, you know, is your data skewed? Do you have class imbalance? For example, if you have severe thunderstorms, most thunderstorms don't produce tornadoes, so you would have severe class imbalance in that case. How are you going to derive your labels in the case that you're doing supervised learning and so on? So there's quite a few questions that you want to think about. And I do go into a little bit more detail on a couple of these. The first one being, if you had class imbalance, so let's go back to the example of severe thunderstorms and tornadoes. Most thunderstorms don't produce tornadoes, and I'm going to try to predict whether a thunderstorm is going to produce a tornado or not. And let's say only 5% of thunderstorms produce tornadoes. My neural network might learn to just always say no tornado, because if I'm using something like accuracy for it to learn, it'll be right 95% of the time if it just says no tornado. So we want to perhaps add class weights so that we end up penalizing the neural network when it gets that minority class prediction wrong. We might downsample artificially, where I modify my training data set so that it thinks tornadoes happen 50% of the time, even though they don't. Simply for it to learn that that's important, right? It has to get that right. So just different ways to trick your neural network into making sure it's actually learning what you really care about for your application.
So how do you, when you have one of your things, how many variables you want? So, but at certain point we start to overfit and have, so how
would you address how many variables?
Yes, if you don't want to overfit and have this, super correlated variables and things like that.
Yeah, you would want to do feature selection, and there's a couple of different approaches for that. In fact, Tom has an approach for that in his notebook. It could have to do with creating a heat map to see how correlated your variables are. That's something we did on a project really recently, and then we found it was like 0.99% correlation. We're like, okay, well, maybe we don't need both. And also comes down to your domain expertise too, though, because for your specific problem, it may be that having a lot of variables, even if some of them are correlated or have 0.5 correlation, you know that we do really need that information in some of the cases. Depends, yeah. And so I'll give an example. I had 20 input variables on a problem, but I had a data set size that was over 1 million samples. So I was like, I have a lot of features, but I have a lot of samples. And I was doing an experiment in a climate change setting where I knew specific variables had a strong shift in distribution and non-stationarity in the different climate states. So I was like, I think having more variables in that case was important. So yeah, it depends. I would say it's not, I would say if you can't say a rule like, if it's 95% correlated, you don't want to have those variables, because again, it just depends. But usually, yeah, having correlated variables. Okay, sorry, I'll stop talking. So next slide. So another way to handle the class imbalance thing is if you can also, maybe you have a lot of samples and you want to grab some samples from there, so you don't end up wasting too much time training with a bunch of samples that are very similar. You can also do this and downsample the minority class, which to me, this seems a little bit confusing, and it's a concept that I struggled with, but it really has to do with converging much faster and how many times is actually going to see a minority class. Maybe doesn't need to see the majority class so many times. So you just train faster and move on. So it can also have to do, your decisions can also have to do with other priorities you may have, like computation time. Thinking about how we split our train and test data. So the data that our model is going to see during training versus during evaluation. If you have any autocorrelation, if there's any seasonality, any trends, these are things that we really have to think about, both in our split of our training data set and our pre-processing, to make sure that we're predicting a variable that we really mean to. So, so for example, here, we may want to split our data if there is some seasonality or some autocorrelation. We may want to do like a split in a certain year, as opposed to doing a split randomly of our data. because we would kind of technically be cheating if we did a random split and there's some temporal signal. Other types of issues include when you do these data transformations. So sometimes you could get away with transforming your data on the fly, meaning I'm training my neural network, and in that workflow, I might apply a min-max rescale. So I might make my minimum 0, my maximum 1. But if I do that on the fly, it may not know what the full range of the distribution is for my entire training data set. And so that might be a time that you want to do that beforehand, that transformation before as opposed to on the fly. And I think for us in the physical sciences, I would say, usually we end up wanting to do it beforehand, where in industry, you might want to do it on the fly if you're dealing with, for example, photographs or something. So it depends. And by industry, I don't mean to sound like industry doesn't also include climate and weather. So I'm sorry. I'm thinking more about like other applications. And then when we're doing classification, we can do binary classification or multi-class classification, and we kind of talked about that earlier. And we have a notebook on our end with Emily and myself where we kind of go into how structuring a neural network differently may impact your results. And if you have continuous data, for example, for your tropical cyclone maximum wind speed, you might have wind speed, but maybe you want to predict the category. So you can take continuous data and transform it to categorical. So I know that might be obvious for some of you, but I just wanted to make that clear. So a common occurrence of binning, it might be, of course, oh yeah, here's the tropical cyclone example. So you might be converting maximum wind speeds into Saffir-Simpson hurricane wind scale. And then going into 2 ways to do this transformation of our data. One is called integer encoding, where we may take some sort of continuous data and then transform it into numbers to represent whatever the thing is that we're trying to represent. In this case, I give an example with colors, but it might be that yes or no might be 0 and 1, right? And I would say we typically don't want to do this unless there is some sort of continuous relationship in those labels, which, yeah, you would just have to assess on your own. But usually for categorical, we may do one-hot encoding where we have a vector that looks like the one all the way on the right. Can you see my cursor? Yeah. So for example, in this case, I may have numerous classes, and each 0 would represent that it's not that class, and there would be a 1 where that class is true for that sample. And then lastly, I don't want to eat into Tom's time, but for neural networks, I did want to go ahead and give you a quick sample. I think there's 2 slides, Tom, on this. And then, so this is what your fully connected neural network might look like. Each one of these circles in the first layer is representing an input variable. Then we have in this very simple cartoon, a hidden layer where each one of these is a neuron. And then here they're predicting one value. And just to give you a zoomed in look at what a neuron looks like, you have your variables going in, they get multiplied by a weight. Those weights get summed. And then we have a bias term that gets added, which is kind of like, just like if you think about y equals mx plus b is your y-intercept. This is a similar concept, so we can shift it. And that gets then passed through an activation function, which can provide some nonlinearity in the learning process before that signal continues onward. A very commonly used activation function that provides nonlinearity is the rectified linear unit. And this is what this looks like. And then a number of hyperparameters exist for training a neural network, and we can go into that in the practical for both our notebooks, and but essentially just to give you a quick glance at this, it's learning rates, activation functions. All of these are different choices that can be made and have to be made by you before you start training. Over to Tom now.
Awesome. Thank you, Maria. The reason I stood up early is that, but I think Milton's getting shocked. I think we can write on this board, which is amazing for discussion. So I don't have blackboards at my university, so I'm very happy we have something. So I have two missions in the 30 minutes we do have. The first mission is to explain a little bit how to train classification and regression algorithms in practice. It's going to stay relatively basic, and then in the last 15 minutes, Maria and I agreed it would be nice to give an overview of physics-guided machine learning because that's a good way for domain scientists to collaborate with machine learners. So if you have your favorite computational scientist in your university and you always wanted to collaborate with them, hybrid modeling can be a very natural way to collaborate and use your knowledge you accumulated over 10, 20, 50 years for some of you. And so let's start. How are machine learning models trained and evaluated? And Maria was super pedagogical. I may not be as pedagogical, so please ask a question if anything is unclear. Okay, so first we need an objective to minimize. If you want to maximize one, just take the opposite of it, and now we have an objective to minimize. So generally, there's different names in the literature. You'll see cost function, you'll see loss function, you'll see error function in some literature. It's a function that maps your predictions and sometimes your truth and your inputs to a cost to minimize. So if you just have your predictions and you don't have any labels, it's this unsupervised learning case that Maria introduced. So for example, if you want to cluster data, you may just want to have an objective that puts points similar to each other together. Once you have truth, you can have what Maria introduced, a supervised learning problem where you're trying to make your prediction as close to your reference as possible. So that's usually the case we are in many of our applications. And if you don't have too much data and it's a relatively simple problem, sometimes you can find a unique solution. You have a normal equation or quadratic programming, but in many cases, we are dealing with multivariate optimization problems, sometimes with messy constraints that are non-convex. And in many cases, what you can do when you have large data and a lot of variables is to minimize this cost, this objective function using gradient descent, where using the gradient, the slope, you take one step down in the direction where it's down. So it's a complicated surface. You're never going to have access to all of the surface, but you can approximate the slope based on the data samples you see. And then all you're saying is like, I'm going to look where down is, and I'm going to take one step in that direction. And then a lot of the algorithms are variant of that optimization algorithm. So here's a nice little picture. I hope you can see it. These are different variants of the stochastic gradient descent. So when you train neural networks, you can choose between all of these algorithms, and you can see, depending on which algorithm you take, they're going to take faster or slower steps towards, but all of them end up finding that slope in that case, except the very traditional stochastic gradient descent algorithm, because it's a bit old and struggling. And so you'll see different names for it. This is more specific terminology if you're interested. Batch means you throw in your entire data set to estimate the gradient. It's not really used anymore, batch gradient descent, because there's large memory requirements. Stochastic gradient descent, in the strictest sense, you would only feed one sample. But usually what we do is mini batch gradient descent. So we have the entire data set, we're going to sample some data, we're going to put it in a mini batch, and then we're going to use that mini batch to approximate the step to take. Now, because it's stochastic gradient descent, you're going to get different results every time, except if you control the random seed. And because you're on a complicated optimization surface, it's rare that there's a unique minimum. So you may get stuck in a local minimum and never find your global minimum. There are strategies to deal with that. So different optimization algorithms can have more or less momentum to like get you out of these local minima, but then usually that comes at the cost of like taking wider steps. So it's an entire art and it's an entire field. If you have an engineering department, it's likely that you have one person working on that almost full time. And so there are many, many options to train and evaluate. I'm starting with classification. classifiers. So I don't expect you to be able to read this table. The reason I put this table is there's this library in Python called scikit-learn. It's a French library actually, and it's a French machine learning library that's really, really nice. And if you just type classification, evaluation, or loss metric, you have this page, and then you can start seeing all the different options you have. So there are basic options, like Maria will show you a binary classification. We usually use binary cross entropy because it has a lot of nice properties, but you know, the sky is the limit. You have a lot of different options depending on the characteristic of your data sets and what you know about it.
So, but if I want to choose one, do you have?
You have default choices. You have default options depending on how your data look and what algorithms you use. And the default option is usually written in the algorithm description. But then what I want to encourage environmental scientists to do is be creative, because that's how you make new discoveries, by coming up with a clever loss function that maybe a computational scientist wouldn't have thought about. And if you look at this page, usually you come up with ideas. You're like, oh my God, I should maybe weigh this tropical cyclone a lot more than others because it has higher impacts.
Yeah, Ryan Lagerquist, if you know about, I mean, of course, you know, fuzzy logic. And so he came up with a loss function that incorporates fuzzy logic so that the neural network doesn't think it's doing really bad if it just offsets precipitation by a little bit, like in a radar image, for example. So yeah. So, and those are things that we've known for a long time, right? When we evaluate NWP, it's just, yeah.
And for the parameterization, I think it's always a nightmare for me to choose how the size of the batch, the landing rate, and the previous slide. Do you have some criteria for recommend people to choose?
We treat them as hyperparameters, right? And we optimize them on a separate validation set. We have examples. I mean, but you know, right? Because you have
no better solution.
And so then you can treat it as, usually we treat it, if you want to get technical, as a non-differentiable optimization problem, right? Where you have different meta parameters that you want to optimize. And so if we treat them, so there's a default choice. You can start with a default choice, and then you can treat the choice of the algorithm, the number of layers, the learning rate, et cetera, as a hyperparameter. Usually what's efficient is you start manual or random. You should almost never do a grid search because that's extremely inefficient, especially in n dimension. So you do a random search, you identify some subspaces that work well, and then you dive in, right? And the way you dive in depends on, but there's libraries with Bayesian optimization algorithm, population-based optimization. But we can talk more about it because I think it really depends on the problem and the algorithm, what the default choice is, and then how you explore that space. But we have examples in the notebook where you're gonna optimize both with a grid search and a random search. I've written both of them in the notebook for random forest and XGBoost algorithms. Okay, so I'm gonna go, this is an example of binary classification. And so the task here, so now going back to the problem of evaluating the classification algorithm. So imagine you trained one, you're very happy. So the default algorithm to train is binary cross entropy. And here your goal is a very standard goal. Is you're given the image of a digit. It's gotten famous because of the MNIST benchmark data set. And you have to say whether it's 5 or not. In a simple example like that, your entire performance can be summarized by what we call the confusion matrix. So if I give you this confusion matrix, which has true positive, true negative, false positive, false negative, which map in atmospheric science to concept we know, false alarm rate, there's all these hit rate, and then there's all these different names that meteorologists have developed for binary classification. This summarizes the entire performance of a U algorithm. So here we have true positive, we happy. Here we thought it was positive, but it's not, so that's a false positive. Here we thought it was not a 5, but it is, so it's a false negative. And here we said it was not a 5, and it was not a 5, so we call it a true negative. And so if you want to summarize how well you're doing, so you need the full confusion matrix to fully know how you're doing. But if you just want one metric for balanced data set, accuracy is a good one, as it compares the number of true prediction to all the predictions. So it gives you a percentage of how well you're doing. And now to give you a feel of how complicated things can get just with a problem as simple as binary classification. And this directly corresponds to what Maria will show you in her notebook. Imagine you use a softmax activation function, which is very standard. So it tells you the probability. You can think of it as the higher the value, the more likely it is to be a 5. So it's going to give you this nice curve. And now you have to choose a threshold. Now imagine 5 was a tropical cyclone. Your goal is to detect a tropical cyclone, yes or no. The algorithm did an okay job at sorting the tropical cyclones, but where would you want to put the bar? Would you want to put it here? Would you want to put it here? Would you want to put it here? Maybe I can do a poll. So who would put the bar here? And then everything on the left is not a 5. Everything on the right is a 5. Who thinks you would put the bar here if 5 was a tropical cyclone? Okay. And who would put the bar here? Okay. And the reason you all answered that is that most of you know tropical cyclones do a lot of damage. So you'd rather miss one. You'd rather not miss one. You'd rather say there's going to be a tropical cyclone, but then there ends up not being a tropical cyclone, but at least you prepare it, than having a giant tropical cyclone come in and not having seen it. And so in that case, what we would say is you care a lot about recall. So you want, whenever you want to not miss any tropical cyclone. Now, if your goal was to search for oil, and it was very expensive to drill, so I'm in a geology department, so a lot of students are interested in that. So imagine you were searching for oil. Then if you're going to send an entire expedition to a potential oil place, you want to make really sure there's oil below your ground. So in that case, they care about precision. And so you can balance these two objectives that way. Okay. Okay, let's switch to regression now. So that was classification, you're predicting a categorical variable. Now in many, many cases in atmospheric science, we are interested in predicting a continuous variable. This is called regression. And the most standard loss you can think of, and I think most of you in this room know it, is mean squared error. And that's a proper loss in the sense that it can only be 0 if your prediction is perfect. That's not true, for example, for correlation. For correlation, I can add 5 to my answer, and I can have the same correlation. So this is the difference between what we would call a proper loss or a proper score if you're doing probabilistic forecasting and just an evaluation metric that may not tell you everything about the problem. So we would typically try to minimize the mean squared error. That's a very, very standard and reasonable choice. Of course, if you have a very heavy tail and you care about extremes, this may not be optimal. If you care about extreme, maybe you want this power to go up, but it's a good first guess. And for environmental application, RMSC and the square root of that and mean absolute error are very popular choice. And the reason they're very popular choice is because they preserve the units of your output. So imagine you want to predict surface wind speed in knots, then your MAE will still be in knots, your RMSE will still be in knots. Be careful, whenever you write a mean squared error, it has units in physics, and that matters, the units matter. So often the problem comes in, someone hasn't done a lot of machine learning, they'll throw wind and pressure together, then the loss function doesn't make sense because you're summing hectopascal square and not square. So always be careful about the units of your loss functions. So again, there's many regression metrics, but I want to directly jump to best practices. So imagine you have data points. These are the blue data points, and you want to choose a different machine learning model. Here it's a simple polynomial model. You have a red model, it's a linear regression, univariate. You have a blue model, it's a quadratic regression. And then you have a green model that fits a polynomial of order degree 100 here, 300 to your data. Which models would you choose in practice and why? So I think that's easy, so we can directly proceed to the vote, because I think you've all thought about this. So who, in that case, would pick the linear model? Who would pick the quadratic model? And who would pick the polynomial of degree 300?
It depends on what you want to predict.
Exactly. Okay, so do you want to elaborate?
If I want to predict some common features, I would like to see the green one.
So the green one would allow you to predict?
Yeah, if I want to predict what is in the middle of the figure.
Correct. So if you 100% sure you're going to be in sample, the green one may be good. But if you look at the green one, even when you have samples very close together, it oscillates quickly and it's not very reliable, right? So the green one is what we would call an overfit, and the red one would be, so that means you've learned the data by heart to a degree where your model doesn't have any generalization ability, while the red one would be called an underfit, which means you can't even describe the data points that you give it. So now how do we assess overfitting, underfitting? And so that's where cross-validation comes in. And it may seem trivial, but if you talk to your favorite computer science professor or your favorite machine learners, if they're doing an environmental application, the way you design cross-validation is going to completely change your result. It's going to change the algorithm that gets picked. It's going to change how you decide it's doing a good job. So that's really important. So for example, here, the way I can see it's underfitting is that, well, I think it has 2 plots. So what we typically do is we break our data set down into 3 subsets: training, validation, and test. That's the most common way of performing cross-validation in machine learning. Training is what you train the trainable parameters of the model on. That's what you fit the model on. Validation is how you choose the hyperparameters, so learning rate, the architecture of the model, etc. And then test set, you should never see it, except at the very, very, very end. And for example, if you're writing a paper or if you're pushing a product, that's going to be how you independently assess the quality of your model. So in that case, to assess overfitting, all you need is training and validation. So here, you can see it's RMSC. And so as you can see that quickly your training model, in the case of the linear regression, as you train the model, it saturates at an RMSC about 1.5, and the validation saturate also at the roughly same RMSC. So in that case, you couldn't technically tell it's underfitting unless you know what we call a baseline, which tells you what a good error is. But assuming you know that a good error is 1, here you can say both models are underfitting. It's not overfitting because blue is not too much higher than red. In that case, however, there's a real difference between the red and the blue error, and that's how you know it's overfitting. So validation can help you assess whether you're underfitting or whether you're overfitting. I don't know that these curves were the clearest way, but if you have any question at this point, feel free to ask.
How you decide it was a large enough difference?
I think in that case, honestly, it's tricky. I think it's because we don't have what we call a baseline model. So imagine you're doing a physical application, your baseline model would be the existing model you're trying to improve upon. And then that would give you a line and it will tell you that error is what I want to beat. And a model that doesn't beat it, even on the training set, is underfitting. Now, if your validation and your test error is significantly larger than your training error, then you would say you're overfitting. So maybe if your training error goes to 0, and then your validation and test error go very high, then you're clearly overfitting. So a good example, if you're on a challenge, your favorite statistical modeler is you give them data from 2 different climates, and you say, the present climate is your training set, and the test set is this really, really hot climate. And then it's going to be really hard for them not to overfit. You can torture people that way.
And in our class, there were like a whole day of just looking at these different combinations of training and validation loss curves, because I thought there were like mainly 2 patterns like you would like, and they were like applying them to their projects, and sometimes the validation curve error was lower than the training error, and I was like, what? So it's anyway, I just wanted to, it's really funny.
And actually, we're going to make you practice in a second. In one slide, you're going to be practicing whether you've understood really what overfitting and underfitting was. So imagine now you train your regression model. How do you assess it? Now you can use a performance metric, MSE or MSE MAE, but as Susanna just said, it's going to give you a number, and it's going to be hard to know whether that number is high or low. So typically for regression problem, assuming you have some variance in your data, we would use what we call the coefficient of determination. It's R squared. Please do not confuse it. If you remember one thing from today, do not confuse it with the Pearson correlation coefficient. Coefficient of determination is not coefficient of correlation. So coefficient of determination, what we use to, but both of them are called R square, which is why people confuse them. So coefficient of determination is 1 minus the mean squared error divided by the variance. So it's going to be 1 for a perfect prediction. It's going to be 0 if your error is as large as a standard deviation. But you can, if your model is really bad, that R square can go to minus infinity. So that's why it's different from the Pearson correlation coefficient, which is the ratio of the covariance between what you predict and the truth divided by the respective standard deviation. And that before you square it is between -1 and 1. And once you square it, it's between 0 and 1. So coefficient of determination, it's a good evaluation metric. Correlation coefficient, it's fine. It will tell you something, but you can maximize correlation without making a good prediction. Okay. Okay, now comes the mini exercise. So, RMSE in kilograms. So I've predicted the mass of, we have to be creative here. Does someone want to predict? Maybe you've, usually I use biogeochemical examples in my classes because of my student population, but here, I don't know. Is there any time we predict anything in kilograms in atmospheric science? Well, let's imagine you were predicting. Sorry? Oh, sorry.
Per square meter.
Oh yeah, sure. So we've integrated over a certain volume, and we want to know how much water vapor there is in a big cube of the atmosphere. So on our training set, we predict 10 kilogram. It corresponds to an R square of 0.6. We validate it using different samples, and we get 0.45. But then on the test set, we get a really large error, and the coefficient of determination is -2. My question is it underfitting, overfitting, or something else? Okay, and I'm going to make people vote. Okay, so do you think we are underfitting? Who thinks we underfitting? Who thinks we overfitting? Who thinks it's something else? Yeah, so it was something else, because if the validation set is properly chosen, we're still getting decent prediction, so we haven't grossly overfit. So there's something else going on. So to give a climate example, what could be going on is you train in the historical climate, you took different sample in the same historical climate, and then you try to predict on a very warm climate. And so you have an awkward generalization problem. And that's part of what I study is like you can have an algorithm that doesn't overfit, but doesn't generalize to new physical regimes or new climates. So that's a generalization error, but it's not overfitting.
But generally, how do we deal with that, with especially climate change? How do we believe a machine learning model trained on observed data for future projection?
Yeah, I mean, that's a lot of my research. I think it's a fun question. If you think you can work in model world, then you can objectively test it by doing pseudo-reality experiment where you say maybe high-res MIP or maybe the pseudo-global warming. Even if it's not perfect, it gives me an idea of the generalization condition that the algorithm is going to be in. And then I use that to test the ability of an algorithm to generalize. And that way you can identify strategies that can generalize to a warmer climate versus strategies that do not.
Are there no algorithms or methods better than others in terms of generalizability?
Yes, those are really good questions. There are traditional machine learning methods that help you generalize. So for example, batch normalization and dropout. So I like to give dropout as an example because it's very easy. It's not perfect, but imagine every morning when you were going to work, randomly 5% of the employees were not allowed to go to work. Then you could never rely on a single person to make coffee every morning. Everyone would need to know how to make coffee. Otherwise, you may end up with days where no one can drink coffee, which is really tragic. So by doing that, you're spreading the learning between the different neurons and you generalize better. There's an entire field called domain adaptation that thinks about how to generalize just from a data-driven perspective. Now, what I argued in the papers we have about creating machine learning algorithms that are climate invariant is that in many cases, we can use physical knowledge to transform the features and transform the problem to make it, to target a mapping that's already climate invariant. And that way, you know, you're going to generalize. So one example I often give is specific versus relative humidity. And actually, I'm going to get into it in a second if we do the physics-guided machine learning, which is the next step. I won't talk about regularization today, but the slides will be sent to the Slack. But it's, well, or maybe I can say, that's an example of how to better generalize as well. What you can do is you can penalize the models for learning too large weights. And so for that, you can use any norm. Traditionally, we use L1 or L2. And if you're thinking of linear regression, L1 norm would be called a lasso regression, L2 norm would be called a ridge regression, and then mixing the two is called elastic net. But you can apply that to any algorithm. Most algorithms have regularization technique that prevent them from overfitting and usually help them generalize. But in my opinion, that's not enough. In my opinion, in physical cases, we can think a lot more cleverly and systematically about how to generalize across climates, for example. Anyways, that's it for the basic machine learning. If you want, I can go quickly on physics-guided machine learning, or if you'd rather, we can go do the exercises. Maybe I'll poll people. Who wants to hear about physics-guided machine learning? Okay, great, I'll go. Okay, so physics-guided machine learning is a particular case of knowledge-guided machine learning or hybrid modeling. And that's a field that's been really taking off recently. And the idea, the way I define it, but I think you can also find several reviews that define it that way, is that we're going to add physical structure to a data-driven algorithm to restrict its output to solutions that are physically plausible. So a very simple example is imagine you're trying to predict relative humidity. As many of you know, relative humidity is defined as the ratio between the partial pressure of water vapor and its saturation value, usually with respect to liquid. And so by definition, it's usually between 0 and 1. By definition, it's for sure positive because pressures cannot be negative. And it's typically below 1 because supersaturation is rare, except at very, very short time scale and very fine spatial scale. So most of you work with data whose resolution would mean that RH is typically between 0 and 1. So how would I deal with that if I was going to predict relative humidity? Do I really want to waste the cost function learning relative humidity? Usually I don't. I just don't want to output any relative humidity that's negative. So then I could add a hard constraint that forces my algorithm to always predict a positive relative humidity. So for example, if you're doing neural network, you could use an activation function whose output domain is the positive real line. The positive real numbers. However, you may tolerate values above 1 because you know supersaturation may happen. Maybe you're working with a pretty high resolution data set and you observe saturation sometime. And so that's when we would want to do a soft constraints where you want to encourage the algorithm to pull the value back towards 1. So for example, this could be done by minimizing the rectified linear unit of RH minus 1, where you gently pull down the relative humidity towards 1. Okay, and so in the examples I gave you, we really in that direction in that case. So I'm going to use the knowledge I have to constrain data-driven algorithm. And you can think, although it's also a good way to test which knowledge is robust versus which knowledge is not that robust. Okay, this is why I wanted the board. So sorry, Milton very kindly got some chalk.
Here is all the technology talking.
Okay, this is everyone's time to shine. Oh, sorry, go ahead.
Previous slide again. I mean, the simple example I understand, but for this kind of example, if you have 3 coupled equations, would that be able to be used to inform?
In many different ways, and there's many creative ways to do it. And I'll talk about it, but the simplest way, which is when people say physically informed neural network, usually they just think about the simple way. It's just you put everything on the left-hand side, so it should be 0, and then you just minimize the norm of the residual for all 3. So you throw the norm of the residuals in the loss function. So that's a very simple way of enforcing it as a soft constraint. So I put everything on the left-hand side, and then I calculate the norm of this, and I throw it in the loss function, so it's that it gets minimized with everything else. So that's why people, when you hear PIN, physically informed neural network, usually people think about this. So it's similar to a Lagrangian for people who do that kind of optimization, and it can be framed as a variational problem for people who like that too.
Would that make the loss function very complicated? Or
yes. And for example, if you know about the neural GCM, which I think is it's Google's first actual climate model with a full dynamical core, but all the physics are learned from data. They have the most, like one of the most complex loss function I've ever seen, where they try to optimize all the things they care about. That's it can be very long and it can be much harder to optimize. And then you have to make awkward choices about how you weight different terms.
At some point, if it's too complicated in the loss function, would that be going back to the physical system, kind of?
Yeah, I mean, I'm going to present it. One of my, I guess, my most famous work is to argue that you shouldn't do it that way when you know you really want to enforce the constraint and you can just build the constraint inside of the neural network. And then if you do it that way, you know that the equations will be satisfied to within machine precision. Okay, but then we can continue exactly what you just talked about. I mean, everyone, like it's everyone's time to shine. What do you think are advantages and disadvantages of physics-aided machine learning? And Ning already mentioned actually 3 in one question, so it's good. But I guess if other people want to chime in, maybe I can take note. Aha, it works, it's really nice. Okay. So I think Ning gave a disadvantages. Maybe it's hard to optimize. Okay. Do people want to give ideas? Yes.
Coherency for the advantages.
Yes, okay. Physical consistency.
Physical consistency.
Normalization.
Oh God, consistent.
He said generalization.
Yeah, generalizability, I agree. These are hard words, so. Okay.
Advantage.
As an advantage, yeah. Generalization, yeah. Yeah.
If you
use the number of training samples.
Yeah.
Sorry?
So I use less training samples.
Less data.
Required for convergence training, etc. Yeah.
Disadvantages could be prior knowledge. I don't want to think.
Well, also, to me, the other thing is sometimes we think we know something, and then we throw it in the optimizer, and it's fighting against the data. So maybe what we thought we knew, well, either the data are wrong, either the problem is ill-posed, or what we thought we knew was wrong. And we can question that hypothesis, and that's when we make discoveries. So I highly encourage you to. Okay.
Wait, you said something?
Well, I was just advantage, disadvantage relative to machine learning only or
Yes,
physics?
just, oh, yeah, you're right. That's a good point compared to physics. Well, I'm just doing it with respect to machine learning because compared to physics, I think it would be a whole other discussion. But that's really interesting too.
So I don't know if it will add to the cost of your computational costs.
Yeah.
Hybrid.
Well, and sometimes it's more cost, sometimes it's less cost, depending on how you do it, right?
I was like,
so if you use physical knowledge to reduce the dimensionality, for example, if you use the equations to only come up with 2 variables to predict instead of 5, then you reduce the cost. But indeed, if you add all these terms in the loss function, you increase the cost. So it's sometimes more cost, sometimes, well, it's hard to optimize here, I think, +1.
How to encode the physics to data-driven models.
Yeah.
The conservative variable are
yes.
For the conservative variable, energy, water, this is conservative in the neural network, in the machine learning.
Well, I'm going to give an example where you can add physical constraint to conserve water, etc. So yeah, so that's one of the advantages, I would say, right? Can enforce conservation laws, and you can also enforce state equations, you can enforce definitions, you can enforce all the things you know should matter in terms of physics. I think maybe that's in, oh, does someone else? We've heard a lot from the first read. Does someone want to chime in from the back or? Like Stella, for example, just to put you on the spot? No, okay. Oh, okay.
Right? So sometimes it's pretty hard to come up with the architecture to inform the equation, the constraints.
Yeah, so hard to encode, hard to design. This is what you're mentioning? Yeah, I agree. It's work. Okay?
So I don't know, when you're trying to make a simpler model than the original physics, is that if you want to simplify a problem, would that be easier or hard to do? Instead of having the full equations, is that a disadvantage, you know?
I think that connects to what Rui says, right? Where in some cases it's harder, in some cases it's easier. If somehow you use these constraints to make the problem lower dimensionality, then it's easier. If you're starting to add all these physical constraints, you can make it harder than you initially intended to make it. So I think I agree with you. It goes both ways, though. Yeah.
It's more case dependent.
Yeah.
We are solving different questions, and we will come out with different physics need to encode. But for machine learning, we perhaps
Exactly. We don't have hardcore machine learning people here, but if we did have them, they would tell you, well, I'll just create a foundation models and it will answer all of the questions you've ever had about the atmosphere. And then you guys can all retire happily. Then we would be really bored. And so, yeah. Okay, great. I think, does someone else want to add something? Yeah.
One of the disadvantage maybe that you think that it is consistent, but it is not. If you have a limited set of constraints, for example, if you put constraints on the wind and pressure, but no constraints on the relationship between pressure and temperature, we can think that you are consistent, but in fact you are not.
Yeah, so it can be incomplete, right? And that goes back to incomplete knowledge or cases where you think you have knowledge, but you may not have as much knowledge as you. So yeah, I think we've covered most of them. For me, another thing is like it can be surprisingly hard to write down the knowledge we have. We don't have that much knowledge at the end of the day when you start thinking about it. A lot of it is empirical. The only thing that exactly holds, in my experience in atmospheric physics, are definitions, state equations, conservation laws. But even for conservation laws, evaluating all the sources and sinks can be really challenging. Yeah, so that's the next point. So that's a bit biased by my thinking. You can have more control robustness, more generalization, data efficiency, interpretability, and then trade-off between physical consistency and optimization. That's a little bit what Ning was, I think, maybe hinting at, is once you add all these terms, maybe you're fighting against a loss function, and then it's really hard to optimize. Okay, and so then just to conclude the tutorial, I'm gonna go quickly through many examples of, because I wanna encourage people to be creative. Often we hear physically informed neural network and we think on one tiny thing, but I want to encourage you all to apply your knowledge in many different ways. There's so many ways we can combine the data-driven modeling world and the physical world, and very few are effectively explored, I would argue, still now in 2024. So I like to put things on an axis. It's a subjective axis. There's many reviews listed here. They'll argue different things. I gave this, if you want the longer version, I collaborated with ECMWF. There's a MOOC on machine learning for weather and climate. It's free and it has a longer version of this. So for me, one of the most physically constrained way you can learn is when you just learn the parameter of a physical model. So this is a schematic from Klima, because Klima, I think, is a pretty good example where, if you know that project, it's between MIT and Caltech, they argue that the external structure, although they've changed their philosophy over time, but the initial argument was that the external structure should be mostly governed by turbulence, eddy, diffusivity, mass flux equations, and so the whole equations are set, and then you only learn what you need to learn. And so then that's a pretty rigid learning problem. And then you only, and you can bring it back to a parameter estimation or calibration problem. So those of you who develop models, you know that you have to calibrate the parameters of your physical model. That can be framed as a machine learning problem because you're trying to find the optimal parameters inside your storm resolving model, which is really hard, or your general circulation model, which is easier if it's coarse. And parameter calibration, parameter estimation or calibration can be seen as a subset of data assimilation, depending on how you define it. So we as a field in atmospheric science are very advanced in that. So there's a lot of techniques that exist. We have entire centers that have a lot of experts, so we're very lucky. We have algorithms like 4D var with deep learning equivalents like 4D var net. That have excellent resources on how to solve that problem. Usually you can bring it back to a Bayesian framework where you're trying to optimize and calibrate the parameters of your model given observations. And using Bayes' theorem, you can bring it back to the likelihood. And then what you're trying to do in general is maximum likelihood estimation, which can become tractable under certain assumptions. And so machine learning can make it a lot more tractable because once you emulate that, then it's much easier to maximize the likelihood of a machine learning model than often the original model, and then everything becomes easier. So you can use Gaussian processes for that, for example. That's a very popular model to solve calibration problems. And then I'm going to briefly mention two machine learning-based framework for that exists. There's the calibrate, emulate, sample framework. So that was developed as part of CLIMA, where first you generate samples from your original model. So for example, you take your climate model, you generate a bunch of sample, then you train Gaussian process to emulate this sample, and then you can quickly sample that entire space of parameters you want to optimize, and then that becomes a much more manageable problem. That's a high-level view. And so if you do it right, not only do you get optimal parameters, but you also get an uncertainty range that can be very precise. So with Gaussian processes, for example, you get the standard deviation, et cetera, in several dimensions. Another one that has been developed by a colleague, Duncan Watson Paris, and the other team is called ESEM. And that one is a little more targeted towards Earth system modelers. It's quite easy to use. So both of them are available. I would say this one is slightly easy to use than the other one. And they use it when they develop Climate Bench, where they try to emulate the response of the climate to different emission scenarios. Now, a slightly more constrained approach, but still pretty, slightly less constrained, but still pretty constrained depending on how you do it, is bias correction of physical models. I think it was mentioned earlier. So I think all of you look at your weather forecast on your phone. Pretty much every agency in the world uses what we call model output statistics, which historically has been multiple linear regression that are fed to the output of your numerical model to give you a forecast that's more consistent with the historical observation. So maybe the model doesn't see that your village is on a tiny little hill where it rains all the time. Well, you train a linear regression to say, okay, because I'm on a hill, I'm going to rain all the time. That's what's happened in the Plateau de Saclay. If you ever lived around here, it rains all the time.
Can I ask a quick question?
Yeah.
For this kind of bias correction, at the individual location, you can use a simple linear regression
Yeah.
bias correction. But how can we use machine learning to capture the correlation?
Exactly. So that's what people do. Like, for example, I don't know, Meteor Swiss, for example, is doing that right now. It's like instead of having one linear regression, usually people will do one linear regression per station, per season, etc. And then machine learning is a very natural way to replace this with just one model where you say, where are you? Which station are you? So you can embed the station ID. Which time of the year are you at? And then it may perform just as well, but at least you only have one model for everyone rather than having to handle individual models.
Yeah, not only one model for everyone, but say if I want the wind field to be corrected, I need them to be consistent because they're correlated.
And so it's machine learning, but traditionally it has been a lot using geostatistics too. Geostatisticians love that kind of problem. That's what they do all day with Gaussian processes, historically with kriging, now with Gaussian process methods. But of course, machine learning can also do that, especially with image processing algorithms. So in that, but in that case, it's not always clear whether it's better to use traditional geostatistics or machine learning. For me, both of it really depends on what your needs are.
So what you call traditional geostatistics?
So for example, Gaussian processes is typically seen as more geostatistics than machine learning. I mean, in the very broad definition of machine learning, it includes Gaussian processes, but in practice, you'll see it's different communities. So if usually in your university, your department of statistics is more likely to use Gaussian processes, and your department of computer science is more likely to use a convolutional neural network. Both of them may give you the same result, they just have different assumptions. Usually statistics requires more work and more knowledge and more derivations, but then it gives you more confidence at the end and better uncertainty quantification. That's my experience. It's just statistics takes more time, but the reward is better, but it's more constrained and it doesn't scale as well with data. Machine learning is very quick, very easy, but sometimes it's messy and it doesn't have good uncertainty quantification.
So I'm thinking like the global climate projection always have bias, right? We know that.
Yeah.
Tropical cyclone modeling, we have to bias correct the tropical cyclone modeling. But I guess heat wave people have to bias correct for heat wave, wind people have to give.
Yeah.
Are there people doing like bias correction to the GCM output consistently so that when we use this model, there's already bias corrected to various variables together?
Yeah, I mean,
possible?
That's what people do in downscaling, or whenever you have the regional climate scenarios as entire field. And sometimes it's called downscaling, sometimes it's called bias correction, but it's an entire field of climate science where they develop those techniques. And very traditionally, they do it with, for example, techniques like quantile mapping. And then machine learning can maybe do more than that.
Yeah,
and it's
learning to more. Quantum mapping is still at one single point. I'm thinking
correct.
Correlation of variables and spatial correlation, temporal correlation, and variables correlation are missing.
Yeah, spatial covariance, like a spatially smooth field, etc. And that's when you can, if you low to medium data, you may want to use Gaussian processes. If you have a lot of data, maybe and that's what we're proposing, very good generative models, if carefully used and carefully trained, can give you a full map of a bias-corrected output. And we have reviews, actually. I mean, we have literature reviews on, for example, I've teamed up with Meteos with people listing all their dream properties of an ideal bias correction algorithm, like multivariate consistency, spatial covariance, like they have a wish list. But right now, there's not a single algorithm that ticks all the boxes. So it's still an open question. But there are algorithms that are much better than just quantile mapping. Yeah. Actually, the lab here, like with David, etc., they have a lot of techniques, really clever techniques for bias correction. Okay. I feel like this is getting long, so maybe I'll just give a very high-level overview and wrap up. So, we talked about post-processing, bias correction, there's nudging that goes in this. And so the general philosophy is this is still decently constrained because if you bias correcting, as long as your bias correction model doesn't become bigger or more expressive than the original model, you're still mostly physically guided or physically informed because most of your signal still comes from the physics model. Then the space I'm really interested in, we do a lot of work on, is models that are mostly data-driven, and then we add as little knowledge as possible that we think is necessary for generalization or consistency. So that way we explore more of the hypothesis space. And so if you want to constrain it, for example, there's many different options. So you could encode invariance or equivariance. So these are important notions. I think most of you are familiar with, sorry, I haven't given this slide in a while, so I don't. So most of you are familiar with invariance. So a good example I like is like, given an image, you're going to have to predict a cat or a dog. If you're just doing image classification, is it a cat or a dog? If the dog translates, you still want to say it's a dog. So that's invariance. So you move the input, there's no response. But often we want equivariance. So if you wanted to say that, if you wanted to find the pixel associated with the dog and the dog moves, then the pixels have to move. And that's called equivariance. And in physics, we have both examples that are very common. And so you may want to encode this invariance or the equivariance in the architecture directly. Yeah.
Say how it's common in physics? Or?
In physics?
Yes, how you do how you're moving, the equivariance.
When do we have equivariance in physics?
Yes, give me an example so that I can see.
Asymmetric tropical cycle, if you rotate it, it's still same intensity.
Yeah, or for example, if
that's invariance.
Yeah, I'm trying to figure out the difference of the two.
Imagine you're trying to predict the response to a point source of heat or of moisture. If you move that source, you want the response to move with it. So if you frame it in a certain way, it's equivariant. But maybe that's a bit too fluid dynamics-y. Do you want something?
No, it's just trying to see the difference between the two. I was trying to get confused.
But I mean, the example I give with a cat and a dog is the same with tropical cyclone segmentation, right? So if you were trying to find a tropical cyclone in a climate data, in a climate data, you would want translational equivariance. If you move the tropical cyclone, you would want the pixel to identify a tropical cyclone to move with the tropical cyclone. So there's some translational equivariance.
So that one you just moving, the other seem that you're just changing the physics.
So this is, that's rotational equivariance.
Okay.
So it's equivariance with respect to rotation.
And the other one is just
Translational.
Okay.
But then I'm interested in, for example, invariance with respect to climate change. So mathematically, if you know what a group action is, you can, as long as you have a group action, you can define an invariance, so an equivariance. So it can be very general, it can be for any transformation, but the common one are translational and rotational. Yeah. I'm gonna write a review on it actually. It should be out by the end of the summer, like specifically explaining invariance, equivariance, invariance, etc. to the climate community, because I feel like we don't have a good reference for it. So, and how to apply it in practice in your neural network.
Also in the machine learning community, people use the invariance and equivariance interchangeably.
Oh, really?
Yeah, they don't understand the two differences for the in the computer science.
Well, except the group that are specifically
Yeah.
saying like Rose-U would distinguish it, right?
Yeah.
But like yeah, but you're right. A lot of machine learners are not very careful, but the group that are studying that are, right? Yeah.
And most people are studying like a material design group that study this like equivariance and invariance very carefully. Like to design proteins like stuff.
But I want to go quickly. So just so you know, there are ways of exactly enforcing state equation conservation laws, etc. We have tutorials, we have papers to enforce conservation laws and state equations and neural networks for the atmosphere. Usually what we do it is with constraints layers. So imagine you have 8 outputs, 3 constraints, you only output 5 outputs, you calculate the rest using the constraints, but then the trick is you write all of this in a differentiable language, and so you can optimize the whole thing. And so when you optimize your neural network, it knows about the constraints as it's being optimized. Now the softer constraint, which is what Ning was asking about related to Ning's question, where that's a traditional method because it's easy to do, it's fast, it's efficient in many problems. You just add it as a term in the laws. You just have to be careful about the weights you put on top of it, which become hyperparameter of your problem. And so it's very common in what we call physically informed neural networks. Now there's entire textbooks on it with code, etc. It became very popular in fluid dynamics. So it's much easier than it used to be. And so in our case, we can do residual of definition, state equations, conservation law. You can have approximate dynamics. You could have spectral loss. So if you know you have to care about certain scales in time or in space. And so that's also being done a lot, and it's useful for weather forecasting if you only care about certain scales or certain time scales. You can do statistical constraints. So if you know you care about certain covariance matrices more than others, you can also throw in the Frobenius norm of your matrix. And so all of that to say that this, and all the references, I'll send this slideshow to you. There's references at the bottom for every type of loss. And so just to let you know that there's a lot of options to constrain your machine learning algorithms. You can also restrict, if you're doing probabilistic forecasting, you can restrict to a given distribution by only predicting the moments of that distribution. And then you can do custom weighting to emphasize certain physical regimes. So for people who care about extreme events, that's a question that always comes. It's like if you're predicting a heat waves, if you're predicting wind gusts, usually traditional loss functions are going to be blurry. They're going to only target the bulk of the distribution. So for example, one of my favorite heat wave paper, there's also nice papers combining machine learning and extreme value theory, but one that's very pragmatic I find recently is by Ignacio Lopez Gomez when he was doing his Google internship during his PhD. He came up with a heat wave prediction algorithm that was really smart. It compared the exponential of y rather than comparing y. And then he showed that that works really well to forecast heat waves.
On sub-seasonal timescale too.
Yeah. Yeah, it's amazing. I mean, I guess we both like it. There's a way to be even lighter, so I'll just finish on the climate invariant example that I presented because I think a lot of you are climate scientists, so this is relevant. So I think a lot about how to make machine learning algorithms robust in a changing climate. In one case that we did for parameterization of convection, was to transform the mapping using physical knowledge. So the standard way to learn parametrization in the vertical would be to map the raw outputs, typically specific humidity, temperature, and latent heat flux, for example, all variables that shift a lot as the climate warms, to subgrid scale heating, moistening, and sometimes subgrid scale radiation, depending on which exact parameterization you're targeting. And so the brute force, what we call the brute force of the raw mapping here, depends on climate. So if I fit this mapping on the cold climate, and then I go in a warmer climate, here you can see in the warmer climate, they get much higher value of specific humidity because of Clausius Clapeyron, and so the algorithm usually breaks. And each machine learning algorithm breaks in different ways because of the way they're built. You can ask me more about how each algorithm breaks. It relies on their extrapolation assumptions. And so what we did is we implemented physical transformation via, you can do it via custom pipelines. You can do it by rescaling the data. If you knew what transformation you've done, you can just transform the entire data set, but you can also add layers. You can do it in the way you generate the data. There's many options to do it. And then we converted these variables to variables that shift a lot less with climate. So specific humidity to relative humidity, that's an easy one. The two other ones were much harder. So for temperature, we used more static energy. Well, for those of you who do thermodynamics, it's a more static energy conserving measure of plume buoyancy. I work a lot with the UCLA group like David, Neely, and Fayez Ahmed, and so we came up with this as a transformation. And then the latent heat flux you can transform using the aerodynamic formula. And then the resulting algorithm works much better. So no matter which algorithm you use to target this, now it doesn't matter, it's a neural network, a random forest, etc. You know that it's not gonna shift too much with climate change. And here we're doing it for parametrization. I think with Jingyi and Colin, etc., we're thinking about doing it for tropical cyclones. And so that's also a way to test theories, like which theories work better than others across climates. And with that, I went way over time, but I hope I encourage you that it's a good idea to combine physical knowledge and machine learning. And I think we're gonna go up for people interested in our notebooks that we spent the night on.
Awesome. So should we take a break before jumping into notebooks? Or we were thinking of doing like parallel sessions where Tom and I would take subgroups and go through our notebooks.
Oh yeah, we'll both be in the same room and people can pick either notebook. And I think we can both help even if people pick the other notebook because we both know all of the algorithms in them. So all notebooks are in a common GitHub repository we have together. I'll send the link on Slack. So you can also do it in your own time, but then I think if it's in Colab, so all the data loads automatically, etc.
Is it in the next slide, the link?
Oh no, that would be clever, right? But I didn't think of that.
Oh. Are you sure it's not there? I thought I put it.
Oh, well, Maria is clever.
So the link is there. And there's an underscore between the 2024 and the Tropicana ML.
Yeah, there's two underscores, right? There's one here, and they're nicely hidden.
Yeah. Yeah, and it's, so my data is from NOAA straight, like text files, so you can see how to read those in, and then.
And for us, it's a mix of the ship's developmental data set and the IB tracks. And Milton, is there anything else?
No, those are two.
Yeah, I think it's just ships and IB tracks. So.
And it's all hosted already.
Yeah, and we have all the data loaders to make it nice for you, etc. And then the shameless plug here, that's a review I wrote for geoscientists who want to get started with machine learning. So which algorithm to choose depending on how many trainable parameters you want, how much physical structure you want, and how much interpretability you want. And it's all in a textbook called Clouds and Climate, which is authored by Sylvia Sullivan and Karina Huis. Yeah.
Very general question. Should we take them first in class into?
Whatever you guys want. I think we're gonna go. Actually, we could. We were thinking of going.
I think there may be more people than that. Students cannot enter infinite.
Oh no, it's good.
Yes. Everyone. Yeah.
the theory that like
Just, yeah, I would come and play. I'm gonna play with it after the fact. I have to go to my seat.
Yeah, I still do.
What time are you in? If you're in a bunch of
For machine learning.
so what is the basic? Have a mathematic Pareto from generators.
Yeah, it's good. And the other thing is I have a
Hopefully I can juste du coup quand c'est fini
So I gotta be on
dans ta vie,
Zoom.
je vais venir plutôt plus tard.
More than welcome to be involved.
No, I think I can join Tom's station.
Okay. So just letting you know, like, that's kind of what we need. Why did you
Je pense qu'on peut d'un côté.
I keep saying we should not see idea of using data and so
So I remind you that there are also ice cream in the freezer.
Probably everyone I mean,
I don't know if we're going upstairs.
everyone can use machine learning models.
Yeah,
I think we probably stay downstairs, right?
all that stuff even for machine learning.
I think we're going to stay downstairs so that you can chat, snack, at the same time.
Yeah, that is interesting. I don't really think about it.
People will get more.
But yeah, the
It's LO.
Yeah,
like
very popular. Everyone studying machine learning.
yeah, I like created this class in the spring.
The 2-year paper. The climate experience more than 4 years.
And for like our major, like we don't even really have grad students.
Okay, are you
Would
And it's named
for now?
What are you two discovering, by the way? Like, what's the title?
Of this paper?
Yeah.
We're not discovering anything.
No, but like putting Stone and Susanna
Attribution.
together. Okay, so that's attribution.
But it's kind of she does
but like the first time was like little
to do an attribution, and she was like, "Oh, if I like attribute everything." You said that in one of your emails, and I'm
So
like,
are you going to write something to criticize attribution methods?
No. So David started this paper when he went to meet Susanna, and then he did not have time to finish it.
Then he said,
"Okay, Stella will finish it." So we had a meeting and said, "Oh, it's good, so nice. Can you write it?"
I guess that's listening. I'm sorry. She was asking about teaching it. Oh, maybe you have an answer. Are you interested in statistics?
I've seen him write. He uses ChatGPT.
And I also listen to the question because you're
like, my question is,
First, like,
why students, I mean, and just to learn, students like statistics, they don't.
I love doing the figures, but I'm really the writer, so I'm happy with that.
For me, for French,
Normally, everyone is
use ChatGPT could change a
So
lot.
do we need to have probability distribution as a foundation for machine
Right, a
learning?
mix of French and English.
Not and why?
To use it in
Not in China. I don't write in
I know.
I have been in the US too long.
A lot of my interns think in French and English
I
simultaneously.
check your probability.
You can write in both. And then it will merge into in English. So it's like really nice.
Like only probability, so I
Put the first draft you pass, even if it's just PowerPoint. If you understand
Now you're in machine
from you. The basic, it can make it.
Yeah, and I don't even really have much time.
Okay.
I mean,
Because of
no, I mean, I've been trying question. I mean, big machine learning models. Regression, that's regression, right? Loss functions, all these things.
Yeah. Oh. I got Well, there's okay.
Still up.
There might be more others in the freezer.
Ice cream.
Did anyone go upstairs?
Why are looking for ice cream?
You.
I think people are mostly interested in ice cream. Maybe we'll just.
Yeah, you need to leave people time to get their ice creams, and then they will get interested in like
Also now
No, but we can probably do it downstairs.
we come to the SST warming.
It's just that at some point people want to come have a beer and not do the machine learning with I disturb you trying to
Or they may participate.
On the model, but the observation.
Drunk enough, they'll start doing machine.
It's kind of like languages thing.
A little bit.
Alcohol and it starts dropping off.
So it's way too long, right? I'm sorry.
And you use machine learning for
not because we are trying to find. PhD is still using machine.
Yeah, we have a full list. Yeah.
Come on, I have a question. Let's say I want to bias correct a model, but no, like projection. That's what represents
were you interested
climate. In like the
before you studied marketing?
I think it's because my PhD supervisor is
substitute the climatology.
When I started
The model with the
freedom. That's the way.
then like each variable is hydrology plus model anomalies.
That's an additive bias. Sorry? Bias correction. Your model is just like the model is just like but it's not even conditional. You do it for whatever the quantile at a constant, right?
Yeah.
Okay.
Yeah. Let's say
That's what we call a baseline. But you start with that. If that works, why would you do anything else?
Yeah.
And then if that doesn't work, then quantile mapping is the next naive baseline that's just a little more clever because it corrects different quantiles differently.
How can I compare?
You score them, so you find that's what I was, well, maybe I wasn't clear enough. Find an evaluation metric that objectively tells you how good you are, and then you use it for different models. And then that evaluation metric doesn't need to be just one number, it can be an objective problem where you look at different metrics, because maybe you want to penalize the bias correction method to keep too complicated. All statisticians will use information criteria to penalize models that make too complicated. So they'll use, you may have heard of AIC, DIC, or not, okay, information criteria. Yeah. So there are ways to balance error and complexity. So with just one,
don't do anything.
The optimist. It works in low data regime.
For my students, so I just know that this is a big idea. I teach risk analysis. So I do probability statistics. So I have the general idea about.
I'm also okay also on your model.
And I don't really know the specific average. I don't do it.
With the actual climate, producing
they put it on
bias correction. Am I trying to like actual climate?
We have very
Still is with respect to what you care about. So if you care about the whole care about just like the delta.
Okay, yeah.
This person. Actually, we apply to design, high school observation.
Then now the really important part is to start complicated models to do the probability. You're gonna have one part where you
I mean, right now they can.
That's well
No, I would think that's an idea for combining physics. Because of now we have web
have a good
Mike and I did use season. So for this, we're just using June, July, August, but for these three variables, you can change them to whatever you would like. If you want to do like post-satellite era, you can change the start date. But this is pretty variable for what you want to do. So you basically read in the CSV using pandas, and then we're going to subset by year with the year start and then the year end that we specified up here. And then we're also going to filter that data set with the year start and the year end by the season that we chose, and then return that as an array based on the LNI anomalies.
I'll quickly add that, that it has this data set has several columns. You can use that link to like open up another tab to see what it looks like. But we're interested in the anomalies, and the JJA that Emily just mentioned, that's the input season into your neural network. So if you were like, I want to produce a mean tropical cyclone season with DJF previous ONI, and get really bad scores.
Yeah, and then this is just what the text file looks like for context. So you have your season, your year, the total sea surface temperature, and then your anomaly. Okay. Maria, do you want to explain the TC dataset?
Yeah, and then here we've got the open TC dataset function. So here, like Emily's example with ONI, we have our start year, end year. For the TC dataset, we're going to do things a little bit differently because we don't have seasonal data. So we are going to select a start month and end month that we're interested in. So here we have starting in August, ending in October. So that's going to give us August, September, October TCs. And our climatology is going to be computed using a rolling window that I'll explain in a moment, which is my ad hoc made up thing to try to smooth some of these TC issues. And I just picked 30 years for that. And we'll expand a little bit more here, but there's your pandas reading in that CSV file, same as ONI, like Emily's example. And then we've got some dummy arrays here that we're just using for helping us with counting how many TCs we have. We then go ahead and use that to filter, and then we select tropical storms or cyclones. The metadata associated with this data set had a list of different categories for nature, but we're interested in this case in the tropical ones, not extratropical or hybrid. And then another addition of the year, simply to be able to group by year, which is from 1955 through 2023. We ask how many unique names of TCs are there per year with that group by function. And that's how we get to count how many unique TCs there are. Then we go ahead and do our rolling mean. We center it, and we are doing a minimum period of 1. So we wanted to return an average TC number for that window for each year. If that makes sense. So the CLIMO increases over time because the TC numbers increase over time according to IB tracks. I'm not saying because of climate change. and then we subtract that from our data set just to get some positive, negative anomalies. And I'll say if you don't do that rolling thing and you compute anomalies, you'll get a bunch of negative anomalies and then a bunch of positive anomalies in your time series. So that doesn't make sense. So again, it probably doesn't make sense this way either, but a little bit less worse than before. And then we go ahead and do an integer encoding where we say we're going to do anything below 0 is below average and everything above is positive. And those are our 2 classes.
Maria, can I ask why you do 30 years rolling average?
You can do 10. Yeah, I basically was inspired by Enzo. You can test different ones and plot what the time series look like. The time series for the using 30 looks much better. Like there was no upward trend. It was at least straight across. And that's all I was looking for.
So when you do 30 years rolling average, so how about in the, so how do you calculate the anomaly in 2020, for example?
So like the first year or the last year you're asking because of the cutoff?
Okay, so it's not centralized.
It's centered.
Centered.
Yeah, but I allow it to be just 15 years in the beginning.
Okay.
Yeah. And the same at the end, you only have 15 because you don't know the future.
Okay.
Yeah. So again, not perfect.
It's perfect.
We're just gonna go with it. Okay, and then you end up with your integer encoding, which is just a array of zeros and ones. 0 for the below average class or below 0 class, and 1 for the above 0 class. And so now you've got your input and output, right? So you have your problem framed. Your input is your oceanic Nino index for June, July, August, and we're gonna predict the August, September, October tropical cyclone activity, whether it's gonna be above average or below average.
Yeah.
Yeah. All right, Emily, take it away.
All right, so this next box, we're specifying our start year and our end year, and then we're running the functions from above, and then getting these arrays. And then we can print the ENSO data set out, and then this should be our anomalies for each year over the time period that we chose. So this looks good. These do look like anomalies. So we can move on to the TC data set. And like Maria said, we did the integer encoding, so these should be an array between 0 and 1. And that also looks great. So do you want to talk about the feature scaling and when we should and shouldn't do that?
So for your input data, usually you'd like to make sure that if you have, for example, multiple input variables, they're all on the same dynamic range. Oh, is it bad? Yeah, you got an error? What's your error? Is that, oh, that's because you have to run the first. Yeah, start here, run that one, click on it, and then the little thing, and then you gotta do each one sequentially. Yeah. Oh yeah, so for your input variable, you usually want to rescale it so that the values are smaller, and this helps with adjusting your weights. And there's several reasons for rescaling, but one of the reasons is that if you have values that are very, very big and your weights are like decimals, and you have a set predefined learning rate, it can take a really long time to update your weights to eventually converge your neural network. In this case, we're using a neural network. Other reasons for rescaling involve if you have multiple input variables, which in this case we do not. But if you have multiple input variables, and for example, one of your input variables is temperature in Fahrenheit, and then your lows are temperature in Celsius, and they are not on the same dynamic range, and you want to rescale them so they're on the same dynamic range so that they're going to have, be comparable to the neural network. The neural network really has no clue what's what, but it's making it easier for the learning. And I'm sure there's other reasons for that, but in this case, because we have anomalies and they're basically really like relatively small, I decided just not to bother with rescaling. But there are two ways you can rescale. It could be min-max, so you can, or many ways you can rescale. One of the ways is min-max, so converting your data to have values between 0 and 1. And then another way is to transform your data so that it's using z-score. So you subtract the mean and divide by the standard deviation. And so these are things you can do, but I decided to not do them here because we're dealing with anomalies and they're all relatively, look like things that I would normally output with z-score anyway, or standard scalar anyway. But I did put them there and commented them out in case you wanted to test them.
And something that I was confused about when I was taking Maria's class is that you fit and transform your training data, but you do not fit your test data, because then it's seeing, like, you fit it to the training data. So it's going to, like, you're basically cheating at that point, because it's like seeing the mean and standard deviation of your training data, like the test and test data. So like you want to like leave your test data pretty much untouched. You want to transform it so that it's in the similar range, but you don't want to fit it to that range. Is that correct?
Yeah. Good point. So you want to make sure when you're fitting the scalar that it only sees your training data set, so that if you're using min-max, it doesn't see the min-max in your test data. If you're doing standard scalar, so it doesn't consider your test data in the mean and standard deviation. So yeah, good reminder. We did not put a comment on that. Probably should add that.
Okay, so now this next box is highlighting the metrics. So these are particularly useful for classification And these are for this is for the binary classification. So here is a whole metrics list available through Keras. There is a lot. So depending on what you need, there's this whole documentation. And if you click on it, it'll give you basically what it does, and then also some helpful examples. So this is like a nice piece of documentation to have. And I don't remember any of these when I'm doing this, but I know how to read the documentation, and that's what's important. So we'll run that. We just have binary accuracy, binary cross entropy, and then true positive, false positive, etc. And yeah, okay. So this next box, this is a little bit longer. So the first thing that we're doing is defining the number of folds, and
you want to start defining the neural network first before we go into the folds. So like
yeah. So we'll go through the model architecture. So we're using Keras sequential, which means that you can build the model layer by layer. So this models equals Keras sequential. This creates the model object. And then first we're going to create our input layer, and we can specify a shape here and then also name this our input layer. We can go and add our hidden layers. So this is a fully connected ANN. So we are adding 2 dense layers here, and we have 4 units. You can put as many units as you want, but we only did 4 because we don't have that much data. So we don't want to do a super complicated model because of our data constraint. And then you can specify an activation function. And here we are using ReLU because our values are between, why are we using ReLU?
We're just adding some nonlinearity.
Adding nonlinearity.
Yeah, so earlier we had the slides, and we said we zoomed into one node, and we said we multiply the input times the weights, and then we sum them, add the bias, and pass that signal through an activation function. And we, in this case, are using ReLU, so the rectified linear unit, and that's simply to add some nonlinearity.
Gotcha.
So this Keras sequential, it's a sequential neural network model.
Sequential is like a model wrapper, so that can you add layers layer by layer, so that's a sequential wrapper for the layers.
Okay, but these layers, they go into our neural network. Is this a neural network?
So the layers, so many layers consist of a neural network.
I see. Okay.
We're like building our neural networks sequentially, piece by piece.
I see. So we're building our neural network model by adding different layers into it.
Yeah, and there's so this is like the API name. So there's different ways you can construct your neural network, but in this case, this is like the most straightforward way, I would say. And so it's just you do this layer by layer. But there's many other ways. And yeah, the Keras documentation details the sequential API and has examples and other APIs as well.
Okay.
Yeah.
And also when you're adding these layers, so are they orthogonal or just?
What's that?
So are they orthogonal or, I mean, because.
Orthogonal?
Yeah, so maybe I don't really. So because when you try to identify this, like a multifunctional, multivariate regression relationship, so you probably can have several parameters. They supposed to be orthogonal.
Maybe you could tell us what you write, what the neural network is on the board, or?
Yeah, I can redraw the nodes if that would be helpful.
Yeah, because this is like, it's almost so simple. Huh?
Well, it's.
I'll let Emily.
Okay, so basically we have
a monitor in your way. Do you want to delete?
I don't want to like move that.
Is there an eraser?
Can I erase your stuff? Do you mind?
I think we can have a Because I would argue the functional API for me is simpler than the sequential. It depends how mathematical you are in your thinking. But if you're more mathy, I find the functional one much easier to understand because it's like a function in math. Whereas the sequential one, it's for people who like to build Legos. The functional one is for people who think in terms of mathematical functions. So these are the two main options.
So our input is the ONI, and then we have the 4 dense layers and then the 4 dense layers. So we'll have and then these are fully connected. So this means that these nodes will all go with each other. And when, this looks so ugly, and when the neural network is back propagating, all of these weights that are connected will be updating. So then this prediction would be or this output layer would be TC above or below, which is the integer 0 or 1. Does that make sense?
Mm-hmm. So in the code, unit equals 4 means we have 4 nodes in this layer. I see.
Yeah.
So the 4 nodes are independent. Are they all?
No.
They would be.
No, they're very much correlated.
Fully connected. Yeah.
Independent, you would need. Are you thinking of a correlation metric or?
You mean so the full circle on the second
piece?
They're usually highly correlated, except if you enforce in the, because these are just numbers. Can I maybe write the function for people who think maybe more mathematically? Because what you're doing, you're starting from your input x, here it's unidimensional. You're doing as you would do for linear regression. So you do a1x plus b1. You're applying an activation function, and that's 4 by 1, so that's why you end up with 4 variables. So this is a vector of size 4. And then there's a second layer, so you do it the second time. So you're doing a2 times this plus a2. And then you're taking a second activation function, and that's ui. And so you can write the whole thing down analytically. It's just a function. And so it's a very simple function with 2 nonlinear activation function. This is a matrix. This is a vector of size 4 times 1. This is a scalar. This is 4 times 1. This is a scalar. So you can count exactly the number of trainable parameters you're going to optimize. So when you're talking about independence, you're talking about these variables. And except in very particular case where, so the coefficient of these vectors and the b's are the parameters you're trying to optimize, and usually these have high correlation, except if you forced them in the loss function to be very independent.
Yeah, and then you can select how many bias terms you have. Like, like that's up to you. Like, you don't have to have the beats. They're usually, I don't know.
I see that they try to optimize as much information you have from the.
This is what you're trying to optimize. These A's and these B are what you're trying to optimize.
This is what we put in the notes.
Yeah, so the nodes are usually think in terms of variables. So if you do ax1 plus b1, that gives you this. So this is a1 x1 plus b1, and so that's 4 nodes, right? Oh, can you see, or am I disappearing?
You're the monitors.
It's a1 ai. So if you write it in tensor notation, there's only one x, right? And so there's 4 nodes. I goes from 1 to 4. It's a1i, because there's 4 elements in a, times x plus b1. And so each node you can think of as one of these variables. Yeah.
Like a full-fitting equation.
And then you fit the whole thing together. And so that way of thinking is closer to what we call the functional API in Keras. And that way of thinking is closer to what we, like the sequential API they built, where you think of it as a neural network and you build Legos, right? You put the first layer and then the second layer. And so when we introduce it to environmental science undergrads, I'll do this. And when I introduce it to math undergrads, you do this.
What does that activation mean?
Activation here is this, well, I don't know. Do you want to also explain or should I go?
I mean, maybe Emily can just continue.
I'm so sorry.
It's okay.
Yeah.
Okay, so then, yeah, we can do the print model summary. So then that will give us.
I have skipped in from the last activation function, sigmoid.
Oh, yeah. So then finally, we're adding this last fully connected dense layer. And we're giving it a different activation. So this will be our sigmoid activation. And this is because we're doing the binary classification.
Yeah. So we'll output values between 0 and 1. So we're just forcing that signal to come out that way.
So then after we create our model with the Keras sequential, we can do a print model summary, which will give us a summary of all of the layers and trainable parameters at the bottom, which will be nice to look at. So then you compile your model. So here we have a set of hyperparameters here. So we have our optimizer, and we chose Atom for this. I think that in Tom's section of the presentation, he went through some of the different optimizers like SGD, and Atom is another one. This is just something that you choose, but you can also play around with and change and see what works best. And the goal is to get to that global minimum that Tom was also talking about. Our learning rate is set at the default of 0.001. Again, you can change the learning rate depending on how your model is performing. You can either increase it or decrease it to get to that global minimum faster or slower. If you increase your learning rate, then you jump around more and you're more likely to pass over your global minimum. But if it's too small, then you can get stuck in a local minimum. So it's just the trade-offs of training slowly with more epochs with a lower learning rate to try to get into that global minimum, or just trying to find that. Yeah, that's tough.
And that will impact how your, I guess in Tom's drawing, on the left-hand side, like how much your A's are gonna update by.
Yeah. And then we are specifying our loss as mean squared error here. And then our metrics are the metrics that we previously defined within this cell.
Can you go ahead?
Also, what do you use MSE? Because you are doing classification 100%.
This is, so Tom and I were having this whole discussion earlier about, so here we're treating this, it's a classification task, but we are outputting everything along a continuous sigmoid function, and we post-process that to say whether it's in one class or the other, but we interpret that as values closer to 1 are more likely to be in the positive class, values closer to 0 are more likely to be in the negative class, and then we have, and so to optimize this, because they're continuous values, we just use MSE, so we can use a regression type loss function, and then there's a second neural network that Emily's going to go over towards the bottom that actually does cross entropy or binary cross entropy, and that one will have 2 classes output. Emily, did you want to explain really quick the loss function computing error, how that's going to work?
You want to do that?
So for MSE, it'll compute the mean squared error, and it'll compare the mean squared error output by the neural network it'll compare the value output by the neural network to the actual value that you know from your encoded label that you had earlier. And so that error will then give you a value. And so we're going to try to minimize that error. And this is just a toy example. So yeah, you might not treat this problem in this way, but it's,
Yeah. And then going back to the model.summary. So when you run this, you'll get this section of the code, which gives you just a summary of what your model looks like. So you can see that we have the the 2 layers with 4 nodes here, and then our last layer with the 1 node. And then it also gives you the total number of parameters, and then also your trainable and non-trainable parameters. So now that we have our model built, we're going to fit our data to the model. So we're calling model.fit, and our X is going to be our input of the training set, and then our Y is going to be our TC of the training set, and our batch size is specified above. So you can, again, choose your batch size depending on how much data we have, and it's anywhere from 16 and 32 are pretty common numbers to use for your batch size, and we went with 16 here. Again, you can change that around. We also specify the number of epochs, and we chose 100. Again, you can increase or decrease depending on if you're underfitting or overfitting, just testing different epochs. And then, Maria, what does verbose mean again?
Oh yeah, verbose will output, it's a choice on how many words to be output during the training process. Here we set it to 0, because we don't want to hear neural network. So 0 is like, shut up. You can put a 1 though. Yeah, and I guess I'll quickly explain also the k-fold. So zooming back out, Emily, if you want to go to the top of that cell. So Emily, I asked Emily to skip over this because we wanted to first understand the sequential API and how we built that little neural network. And the idea here with building a neural network and training is that sometimes you can choose a certain subset of your data set to be your training data, and then hold out part of it to be like your test data or validation set that you're not going to be using for updating your weights, but that can impact what your neural network learns. And depending on how you do that split, your neural network may learn something that's not generalizable to the unseen data. And so you can test how sensitive your neural network is to the subset you choose. And so here we're going to do cross-validation, and it's we chose 5 folds. So we're just going to grab 5 different subsets and hold. We're going to train 5 different neural networks, and for each one, we're going to hold out a different part of the data set to be the validation set. And then the rest will be the training set. Emily is going to go ahead and...
I didn't understand what Maria was saying until I saw this, so this might be helpful.
So one example is this. Let's say you had the top row is your entire data set. The pink text is your validation holdout, and your white text is the training set.
It's the most important.
Where's your test set?
Yeah, we're ignoring that right now. Okay, yeah, and so here we chose 5 folds. You can choose more or less, and you can test what that does.
But then this test depends on the, like, is it 1/5?
It's 1/5. Yeah. It'd be 1/5. Yeah, approximately. Yeah. And here in our k-fold, we did shuffle true, which might be an issue for our data set if there's autocorrelation. So remember, for us, each sample is 1 year. So try both. Yeah, try setting it to false and seeing how bad it gets. But go ahead. Are you already trained?
Yeah. Yeah, so then for each fold, it will give you the score. So our loss for fold 2 was 0.249, and then our accuracy was 57%. It'll give you that for each of the folds. And
one of those was worse than a flip coin.
Yeah, some of them were not too good, 42%. Not looking too good. Okay, so then we are plotting.
What are good results for that? I mean,
what's that?
What are good results or values for a good training?
Yeah, so that's going to depend on whatever baseline you choose, right? And what state of the art for your problem, perhaps. Or like for me, I'd look at this and be like, yeah, doing worse than random is very bad. But this goes back to the broader point about cross-validation, and I think more importantly, it's that do you want to explain the optimization or optimizing versus?
Yeah, so if we plot the first graphic, we have the number of folds, so 0 to the number of folds, so then we have all 5 of our neural networks that we trained, and then this is our loss per fold, and our loss function was mean squared error. So if we compare against mean squared error amongst the 5 ANNs that we trained, it looks pretty consistent. But
so that's pretty good in terms of the thing that we're optimizing isn't too sensitive across folds. But
when we look at our accuracy, that's when we start having some issues across the 5 neural networks. So then it's like, what are you prioritizing? Like, do you want a really good mean squared error? Do you want good accuracy? It's dependent on what you're prioritizing.
Might get different results for different objectives.
Okay.
And if you're not optimizing on a certain objective that you really care about, that's something to consider in how you frame your problem. But yeah, but you can see it on the thing that we're optimizing, right, isn't that bad among our 5 folds, but then accuracy is not good.
Yeah. Yeah, so these were just kind of some of the questions that we came up with were, again, like looking at those hyperparameters, how does changing some of the hyperparameters impact the performance? So you can change the batch size, the learning rate. Is data augmentation going to help with any of the skill? And does reducing regularization impact overfitting? So I think Tom was talking about dropout earlier, so maybe including dropout or doing a batch norm would be helpful for this problem. So now, instead of using the integer encoding, we're going to do the categorical prediction again, but with the one-hot encoding. So yeah, so this cell here is taking, again, another keras function with the category encoding, and its output mode is the one-hot. So we're inputting our one-hot layer into this TC dataset. So our TC dataset was the one that was outputting the 0s and the 1s. And instead of doing the 0s and the 1s, we're going to do the one-hot encoding instead. So it will look like, so this is our TC dataset, just the first 5 integers with the 0s and the 1s. And now when we do the one-hot, it shifts those into the array is now a different size. So we're doing, the first one was a 1. So this is now outputting as 0, 1. And we defined our type as an integer here. So then our second one would be 0. So then the one-hot encoding for this would be 1, 0. Does that make sense?
So it's putting a 1 at the position of the class where the class is true. So the first position is the negative class,
for the 0, and then the second position is for the positive class. So that 1 will just be wherever that class is true. Yes. So if you had 10, it would still be a bunch of zeros, just a 1 at the position. Yeah. So now we're going to build a model the same way. We have our model that we're initializing with the sequential, our input, our 2 dense layers with 4 units. And now instead of doing the 1 layer at the end or with the 1 node, we have 2 nodes because we now have 2 categories with the 1 hot encoding. And instead of using the sigmoid activation function, because now we have a multi-class classification problem, we're going to use softmax as our activation. We're going to print out our model summary again, and then we're also going to compile the model the same way, except for our loss, we're going to specify that we want to use the binary cross entropy from Keras, which is our categorical loss function, and then also use the same metrics that we previously defined. Then we're going to fit the data to the model. So we're using our same input for our ENSO data set. However, for the Y, we're now going to use our TC1 hot instead of the TC data set with the integer encoding. Our batch size is going to be the same at 16. Our epochs is going to be 100, and then our verbose, we're just gonna keep it at 0. Yeah, so then we're going to do the same thing with the folds. So basically anything that was TC_DS is now going to be TC_1 hot for our input. So let's run it. Yeah, and then we'd also change the TC1 hot up here as well. So then we get this nice model summary again. We have our 2 layers with our 4 nodes, and then our last layer has the 2 nodes instead of the 1. Again, because we now have the 2 classes that we're predicting. And then the fold summaries. And now we can do the loss. So again, now our loss is not MSE, it is the binary cross entropy. So as we can see, it's pretty consistent over the 5 neural networks that we trained. And then when we look at the accuracy, it's pretty variable. The first one did very well and then deteriorated after that. And now I'm interested and I'm gonna change the shuffle to false and rerun it.
Yeah, and so I think maybe the bigger question that this is meant to raise is, well, there's 2. I guess for me, something I'm interested in is what happens when you have multiple objectives and you want to find a neural network that performs pretty well in both of those objectives. Right, and in that case, you might have a multiple objective problem. And I think in the talk last week, I shared some work from our group where we're working in that space on selecting multiple objectives and finding neural networks that are in that Pareto space where you're Pareto optimal among multiple objectives. Or you can, some people like to just put multiple loss functions into one loss function, then you can't really disentangle them very easily. And then I think the other question this notebook is meant to raise, and Tom was saying that some of his students use this to say when a problem is not tractable with
You can talk to Milton and Frederick at length about it. They love, I mean, most of my group now does this, yeah.
Yeah, so you might say, you know, if you have something that looks like that, where accuracy is very poor for certain folds of your data, then maybe this problem is either ill-posed or too sensitive to your underlying data structure, because if you change the validation set, suddenly your model performs way differently. And what are some things you might do was it you? Yeah, do you want to give suggestions? Like, so here I guess something I have a question about is if we are optimizing on one objective or we're using one loss function. Okay. And that one loss function is giving us very consistent results across folds. And then we use a different metric, which is not being used as a loss function, and it gives very inconsistent results. What would you do? Right, because it's not being used for the loss, the other one.
I would, if I get that kind of behavior, one of the things that I would check if is an underlying difference in the distribution of the information in the folds that would be captured by one metric but not the other. Right?
Can everyone hear that? Because that's pretty nice. No? Yeah. Oh yeah.
Just because if you're trying to classify these into very simple, like it's intensifying or not intensifying, but is it because you have like a higher prevalence of one, like very strong storms in one fold and not in the other, and so it's messing up with a like subset that isn't being captured? But I don't know, Tom, what do you think?
Also, maybe is the second, if you really care about that metric that's highly variable, another possibility is that you didn't choose a loss function that was aligned with your final objective and you just have to weigh it differently, change the loss function.
Yeah.
So that's assuming you care mostly about the final objective and not the previous one. So it depends about.
Totally.
Yeah.
Yeah, I was saying earlier that you could even like combine the two objectives if you really care about those two and they're different properties of your data.
But then you have to also like figure out how you're going to balance the two, because then you're going to be like hitting the optimizer trying to do two different tasks that it might not want to converge to.
Yeah, and then we're back to Pareto optimality.
Sorry?
And then we're back to the Pareto frontier.
Yeah, and so the nice thing is maybe that's a good transition to is that the final plot of the notebook?
Yeah, and I think
the next notebook revision, the next notebook we provide code to like Pareto fronts.
Oh, you do?
Yeah, so the final at the very end, I have code to put all, because we train a lot of models in our notebook and then you put them all in a Pareto front. You choose which ones you prefer.
The hierarchy.
And so, yeah, we have a whole machine learning model hierarchy. And so you could take that Pareto code and use it here, and instead of doing what we do, which is complexity with number of parameters and different losses on the test set, you could pick those two losses that don't behave the same way and see if, and it's really useful because then depending, so this is at the heart of the paper Maria, I think, is writing and will be out soon. So maybe I'm like, we both writing on Pareto fronts at the exact same time for slightly different purposes, which is funny. So I think both of us will come.
It's not the first time you are working on something. We're both working on something.
We have a generalization thing, and then we both, okay, yeah, okay, well, it's good. We agree on many things.
Tom's are always high impact. Mine are.
No, Maria, that's not true. I cited yours. You got yours out first.
Wait, but then Emily.
So Pareto is when you're trying to optimize compute. Oh, sorry. If Emily, I'm only want to speak if you're done. Are you done?
I'm done. Yeah.
Okay.
And then there are some Q&A, but I think everybody's good now on the notebook. So yeah, we should share Tom's. Do you want to put Tom's notebook on? Yeah.
Or maybe it's easier if, Emilia, you're going to go through the regression notebook, or is that going to be me or Milton?
I think you can at least like share it really quick.
Yeah, I can. I don't mind.
Okay. But just like the quick advertisement for the Pareto front is like, it's especially useful if you have competing objectives. So let's go back in Maria's case. There was a loss function and there was this accuracy metric. And well, it's easy if they both go in the same direction. So loss, so maybe minus of the loss function. So, and then in both cases, you're trying, well, let's do the opposite. I'm going to do 1 minus accuracy.
Yeah.
So in both cases, you're trying, your goal is to go here. That's where you're happy. And so then if your models fall like this, then that's kind of a trivial case because like the models that are better at the loss are better, like have better accuracy. And in that case, it's easy because you know that by optimizing your loss, you're going to go in the right direction. But now, you know, if something is wrong with these two are competing, so in our period of front, complexity is competing with error. More complex models can get lower error, but then they're less interpretable. Then you're going to get something that's like this. You're going to get a bunch of models here. And so then you're going to get models that are very good at the loss, but they're very bad at the accuracy and vice versa. And so then you can't choose a single optimal model. And so all the models, like the Pareto front is defined as the set of models where you have to compromise a metric if you're trying to improve another one. And so what you do is you just draw a staircase. So beam, 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 beam. And that's your Pareto front. And so any model on that front is optimal with respect to the multi-objective problem. And then if you care more about accuracy, you're going to go here. If you care more about your loss, you're going to go here. And so that's a complicated case where you're trying to optimize things that don't want to go together. And then the nice simple case is when things line up here, and then everything goes together and we're all happy.
Yeah, and you have just one model that's optimal. Hello.
Should we be releasing humans?
I think you should be releasing humans, but the machines can stay. No, but I mean, you can continue. But just to say that if you want to start to help yourself, I think you can.
I feel like we could combine the two, no? People can come and...
Wait, oh, is it happy hour?
I mean, France is not a working culture. I'm obliged.
Oh, right.
After 5 p.m. So I'm obliged to release you, otherwise I can have inspecteur de travail, like people that come.
Can be
like,
two Americans where it's like, we'll work as we...
Very good working colleagues are like...
Okay, should I?
And actually, me, I have a meeting with the students.
Are you working after 5? What?
I think we can hear.
Want me to run this stuff as you're talking?
I think it's going to take too long. I mean, I think if you're going cell by cell, it could easily be a 1-hour notebook at least. So I think I'm just going to give the general philosophy.
Okay.
So general philosophy, you can open it in Colab. What it does is it uses the first. I don't know if Milton wants to come. Milton? We're going to give like a 5 minutes overview of the notebook, maybe.
Milton is the other Nicaraguan. I am the other Nicaraguan. We are two.
We are two from Nicaragua. Do any of you want to? Dynamic. Okay.
Milton is also the author of TC Bench, a new benchmark dataset. And what happened right before this notebook was he made the first pip installable version of TC Bench. We're super happy. And so thanks to this set of utilities, what you can do is you can load the data set in a way that's very nice and straightforward. And it's organized by tracks, by storms, and it makes it all really easy to manipulate. So basically the first part is loading TC benchmark 0.0.3 RC12.
I like the precision of the 0.0.3.
RC.
Release candidate. So all this started with 0.0.1, and then I realized, okay, PyPy doesn't let you overwrite, and you can't delete and then just publish 0.0.01 again. And there's only so many 0.0 alpha versions that I want to put out, and so at some point there was a suggestion for like someone wrote RC on theirs, and I'm just like, okay, release candidate. And so you can see that it took me 12 tries to like debug for the notebook.
But eventually we'll get to 0.1, which we're really excited about. And then we do all the other imports, and then if you scroll that, maybe you can run as we go, I think. I mean, it's going to install a bunch of stuff. And so, okay, so here we, so that's a screenshot of how it should look. And so what we did is, because it's a lot of data, what we suggest is you create a shortcut in your Google Drive. We have instructions, it takes 10 seconds, and then that will load the data set efficiently. Otherwise, it would take too long. Otherwise, what I typically use was Pooch. Yeah, maybe you can demonstrate.
Yeah.
And so then it's.
Let me go back to the instruction. I didn't read it.
Perfect.
This is like stressful to do in front of everybody. Oh, I'll put it in data. That's perfect. Oh no, wait, should I not have done that?
Yeah, shortcuts, and then you would add it to my drive.
That's the easiest because then also you can.
Look at that.
I was trying to be organized.
I mean, you can send it to your data folder. And you just have to change the path.
Oh yeah, no, well, not
This is just like to make it
extra work. So once you do that, then it should be really quick to load the data. And so the advantage is here you can load years and years of tropical cyclone seasons. So here we're gonna load like you can change your parameters. Then you do continue.
More than 10 seconds.
Continue.
Then you continue. Their private information has been.
But an alternative is to use, if you really care, if you really want to avoid, I mean, it's a pretty safe Google Drive, but if you really are afraid, you can use the Pooch library in Python, and Pooch will allow you to download files with less interfacing, but it's going to take longer because it's a lot of data. And now you can load specific tropical cyclones, specific season, and then if you run these, so it should be quite fast, and then you're going to get to a point where it tells you, okay, which season do you want to load for which basin? And I think the example we give loads 2010 to 2019. And once you load the season, the overall philosophy is quite straightforward. You're just trying to predict intensity and pressure changes with a 24-hour lead time. And we design a scoring function for you, and we design a training validation test split for you. And then the notebook gives you an entire hierarchy. So I had a lot of fun last night, and we have an entire hierarchy of machine learning models and strategies to prevent them from overfitting. So I introduced sequential feature selection to just select the couple of inputs that lead to the best generalization. I introduced regularization technique. I introduced hyperparameter optimizations for different algorithms. But I'm starting from very simple. So we're doing it for multiple linear regression, random forest, XGBoost, etc. But I set it up at the end so that it outputs a Pareto front so you can try to compete with the models that are out there. So we give you a lot of models, but the data is all there. So if you want to train, and I give a couple of suggestions, you could train a polynomial model, you could train a model that takes memory, so it takes more than one type step, but it targets specific variables. So we've also included explainable AI plots. So it can tell you which features are more important when predicting tropical cyclone intensity and pressure changes. So you can see, okay, Vmax and MSLP are really, really important. So you could take more information from these two variables. And then at the end, I have a function to show you all your models on a Pareto front automatically. And so you can see where you fall on the Pareto front if you come up with your own model.
Can I make a question about the data itself? So I know I'm annoying about that, but the Western North Pacific, you have the USA and then the WMO data. Correct. And then if you use one of the other, you have big difference in intensity.
Yeah.
So how do you deal with that when you do your intensity, your training of your model?
So the intensity that it grabs by default, it grabs the US agency representation.
Always, because otherwise the covariate, we don't want to deal with the covariate shift.
No, and also the
different definition.
AMA has
the difference in the definition.
By the systematic lower than the.
Yeah, and even in the North Indian Ocean, they have different averages, so it's a nightmare. So we just take USA winds because it defines the same for all basins.
Good. You made a good choice. I'm just.
I feel like you gave us this advice 2 years ago already.
Okay.
And we took it into account.
Okay. I forgot.
Because you did write on that document too, 2 years, like a year and a half ago.
Okay, good.
Yeah.
Just checking.
No, it works. It's much better. Otherwise, you're doing crazy stuff.
I know. Yeah, but people do that. They don't even realize that there are multiple options for in the IB tracks. So they just say, I'm using IB tracks, and I say, but what? Which option? Which like?
Yeah, for those of you who don't deal with IB tracks on a daily basis, there's different definitions for how to measure the maximum surface wind speed. And so depending on the basin, there's different averaging times, which lead to different variables. So to be consistent, you can always use the USA underscore winds field that always has the same definition. And then you're comparing apples to apples and not apples to pears and oranges.
So the official agency for Western Pacific is the Japanese Center, JMA. But they do a different average, 10-minute average of the winds instead of 1 minute.
1 minute.
Average. So their winds always, even if you do a transformation, there is supposed to be a transformation from 1 meter to 10 meters, there are still differences.
And you introduce more bias. For machine learning purposes, the transformation ends up usually introducing more bias than what it's worth by training on multiple basins. So you have to train on each basin separately.
Computation takes a moment because you are doing 10 years.
Yeah, so the reason this takes a while is because it's 10 years of data. And then maybe Maria wants us to stop, or is it the question?
Do you think we could use an embedding layer for each basin? Or train it?
So what kind of embedding layers?
Or condition it? Like a conditional neural network, but conditioning on basin?
I think it would be nice because the basins have different characteristics. Like the Western Pacific, you have the most intense storms.
Include the latitude, longitude as one of the predictors.
Yeah, we did that with the random forest thingy.
But I think the idea that you were suggesting is a bit more elegant because, well, I don't know, you also kind of want to enforce it as a strong constraint, right? Because because you're kind of throwing noise because it's as if the Y was defined completely differently. So you don't even have the same Y variable.
But there's some similarities, right?
There are some similarities. So what you suggest is fine. I would, exactly what you said, I would put a basin ID.
So like what kind of structure you are using for your model?
Like, so this is very simple, right? Here we're showing a whole hierarchy, starting with a multiple linear regression and progressing all the way to XGBoost. But this is a really simple statistical forecasting setup. For longer lead time, our current philosophy, I mean, Milton presented this to post-process neural weather models because you need the global context. Like as soon as you pass 24 and 48 hours, if you don't take into account teleconnections, you can do it via indices. But if you don't take teleconnections in some way, you lose predictability. So at you end up regressing to climatology really quickly if you don't take into account the global context. So here we're in a 24-hour lead time, so you can get away with just taking mostly local contexts into account. But as soon as you go past 24, 48 hours, you need the global state of the atmosphere.
So does your model get better intensity forecast than the standard things that's used? Like
not in this notebook, because that's pedagogical.
No, I know, no, but he's doing the real thing.
The neural weather models, I think we're getting competitive results, but it's really tricky to compare it to ships because it's a dynamical statistical forecast, so they use GFS. So then you're not comparing. It's hard to make an apple-to-apple comparison because using GFS assumes you have the whole GFS forecast available, which is not the same as post-processing neural weather model, because neural weather model, you can run it yourself. So you can do the forecast yourself and the post-processing yourself. GFS, you have to go grab a dynamical forecast output and then post-process it, which is, I would argue, a different exercise in nature.
But I'm just wondering if, like, are you in the ballpark of things like ships, or as much? I was just curious, how far are you from using something like ships?
That's a great question, and I wish I could have an answer for you.
That's exactly why we're doing TC Bench. We want numbers that are as precise as possible. And so by the time we finish TC Bench, which is in a couple of months at least, ideally early next year, because we kept discovering new things. So we've been working with Mark and Kate.
No, I was talking to Susanna and the previous.
And it seems like every 2 months we learn something new, but we feel like we're getting really close to having an apple-to-apple. So.
And you don't want to do a hybrid model kind of setup like ships.
If we want to do hybrid with the model you can run yourself.
Can you transform them differently?
With your neural weather model, you can run yourself because you can just run it on your laptop.
You don't want to grab GFS, that's what you're saying.
I mean, I wouldn't be opposed to like having the score that you can compare yourself against other variables, right?
Yeah, so to the score. But maybe
provide the data from like GFS I mean, I guess you could treat it the same way.
But it would be a separate category and we would have to make it very explicit.
Yeah.
Because this is pure, in this one, and that's the first example in TC Bench, it's pure statistical forecasting, so you're not allowed to see any dynamical model in information.
Some of the forecast that were purely statistical, yeah?
Yeah, I think because now even Ships is not that competitive. Ships is using the consensus forecast. So I'm imagining if Ships is using a lot of geographic information, like so downgraded that it's in the 2000s, Ships was thing, right?
Yeah.
I mean, I guess
You're like,
And if they
yes.
was something of like lines can do weird.
I'm assuming can read what they used to do in the past. Go back to PPM, just like I'm wondering, just like you have a comparison that's just how well you're doing. That's.
I don't know if you wanted to say anything.
Yeah,
That's
so
like,
I'm
just running off.
You run all of it. After the data preparation, that's all Tom.
Okay, so but that's dynamical one. I want like if you get.
And then eventually it gets to the Parade front.
Okay, cool. Statistical models that they use to.
But the idea is that, you know, they prepare the time series.
you get a baseline, but I would say that I'm not too worried.
The Western Pacific instead, you just change the.
I mean,
that's why it takes so long, because it's generating a time series that you are in.
Okay.
That's right. From the ship.
Add them to the
I never worked in that time series. I remember seeing this that I don't
like coffee or latte or something.
But it should be pretty. I think. Well,
yeah, so that's what I was. How far are you from what?
I guess, sorry, if you say you mentioned the entire team. If we take the
Yeah,
entire
but-
team,
yeah,
the best person in the team for that Pascal right now is Mary McGraw, if you know her.
Name, I don't know.
And her random forest.
It's better than.
The problem is she was alright, so she compares herself with the AI forecast.
Oh, yeah, better than.
All right.
Yeah.
Yes, better than she.
I'm so tuned into this.
Yeah, so that's alright, so it's like right, I put her random forest in, but I made it a regression.
Yeah, so it's,
as good as it's like very evolving right, which it works directly with it's called a question. Whereas we get one question every 2 weeks. I visit the third
our the correction with other variables.
And how about the diversity?
Yeah, I mean, we could, and the cat, like a weighted shift.
Have all the metrics have a bit nice and what meaning for it. It has all the evaluation. And it's Rob DeMaria is converting them in Python, right? The son of Mark DeMaria. Yeah, so Mark has a son in the research scientist that was very good at computational stuff. So he's converting all the Python and HT packages to Python. And then as soon as that's done, he'll bring it to us and we'll make them part of GCDF. That's the evaluation metrics.
But they also give you data from their models in the past.
Well, at least we have the right.
Because for you to compare.
Is it still closed?
You keep blocking data.
One dynamical model, whether it's IFSA trip.
I'm like, sometimes it's like a reflex to just, you know, like close the door behind you and look at opportunity because how is it getting closed then?
Probably. And you're going to close the evaluation. Globally was early.
Right.
I mean, with a per basis.
Because also because yeah, so that's what I'm saying. I would.
Oh, you mean the least time?
Yeah, so I don't think
then
that
Me, I really didn't want to have on purpose.
Yeah, so I mean, probably
still just for the evaluation purpose, like, you know.
But I kind of I see it as a strength of it.
Yeah.
I came up with this idea yesterday.
No, and I'm just not saying, I'm just.
So this is another question that I would enjoy having develop something based on culture. Very happy to
Video with.
Give me more data and I'll just stick more data on there and we'll play around and create and yeah.
Yeah, so like I would like to try play around
Yeah, the development organized. Half of those.
Oh, I'm sorry.
I don't want to say it's fine.
I mean, it sounds fun.
I love that. By the purpose. We spam.
Running this?
Yeah.
I want to see the prototype of them. I'm there now. And so with the idea that they can learn the science. So that they can.
Okay, yeah.
No, it's so
Trying her best.
and everything.
Okay.
So, but.
Oh, yeah, here we go.
So sometimes some basins do some things right.
I would say they don't exactly. It's very.
So there's one for each variable. Yeah.
Basins, but I like. If you want to, but you don't run it. You don't run it.
Okay. Yeah, we receive it.
Right. And you run out of it. Like highest, I think product peak would be there.
Oh, it's harder. Yeah, but it's also overcrowded. Like there's a lot more people working on it.
I'm just saying, you want to show your model works.
No, I agree. It's the highest spot by far.
Yes.
That I'm with you. Like
Yeah, exactly. That's what I'm saying. Yeah. So I would do that.
For a causal feature selection, the causal models we work, which is much less high performing than post processing the model, right?
Very human, boy.
Yeah, very progress on adding or removing everything with Sierra. And Mark and Kate will not tell me if they have it. But it's so nice and patient with us. I think it's because maybe they don't have.
I don't know. I know the name, but I don't know. Like in person, I'll never. Yeah, I know the name. I have, you know, I don't know the person. So it's like I don't do a lot. For the weather.
But as a whole, like some of the other Syria people, people are scary. I mean, no, I don't.
You're afraid of the competition. But I think part of it they are very.
Small data when some transfer register.
My job. I'm just saying.
And then do you
voglio buttarmi da un po'
I think I might have to dip out.
I understand one part is that.
I don't think I would be enjoyable. I am no.
Stop. So I know that. No, this is like my
What's with goat cheese? Is there goat cheese inside?
There's a lot of
So I
would be hard.
Yeah, bring it down there. I can sit down, just go back to it. To know what it looks like.
Eating was probably my favorite part of the Me too. I never. All these people I know the name.
but I
She
never.
was just so like quick with it too.
Yeah. Well, it was like you had just put the first handful in your mouth.
Trying to improve.
Yeah, the timing. Perfect.
There are tickets to go to the second floor. You have to climb.
Casting or something?
We were just trying to get the.
Like you wanted to work out this week. Or we're also, there's also the possibility that there might, you have to go up to the window and ask. There are tickets to the top. I think on the fees are there.
Yeah.
Going to the window.
I'm fine with that.
Be like,
Even if we want to do the stairs, we could probably just get the ticket there.
exactly. There's so many tickets available for the stairs. Maybe we just go where like.
But in the end, it's trying.
We try, whatever.
There was something.
Like, you know, I'm South Korea.
Some things there.
I should go put some makeup on. But it's only based on my Uber Eats people take a whole lot.
Yeah.
So the step tonight. You were super tired. Didn't have any makeup that day too. That's not bad. I think you can steal. Even
As an example of bias data set because papers like.
So and
We always collaborated because I mean we.
I know, but they're going.
This is my emoji thing. This is excited. It's a cute. It's a fun thing. I really like them. Like they do a haircut. I don't know why they have this emoji. Sometimes you see it. Yeah, this is the Chinese website.
Good. I think people just have it.
You can have whatever animals. Have anything.
Mind that.
How can you send it if you don't have signal?
Because they have
Yeah, it's super good. And you can add whatever flashes from different emoji artists.
Et en fait, ils ont changé.
Maybe too many. I don't know.
I mean, I think I could be an emoji artist.
Yeah.
Not that one. The other one.
Yeah. I think these are small, but they're looking good. What?
They are linked.
Yeah, look at this one.
Mark can push you like her back, right? I'm not gonna there's a lot of work to push things through, and I don't have
They have a patent on
Tomorrow, I think it's far as like kind of like today.
I think a lot of hope, right?
the emojis.
Try to go to Montmartre.
C'est entre les deux. C'est hexagonal. Donc c'est pas évident.
Art and
uniforme.
Hi.
For your board
In there. This is just but I want to. But I want to.
Yeah. It's the dinner and like a lot of like free time.
Yeah. So we can do this if you want.
Yeah.
Like a company name.
I think that you can just do, yeah, and then it should say, yeah.
Let's see what's happening.
Where do we play?
Toulouse.
No, it's between these options. Africa, okay.
Machine learning and satellite data.
That's automatic. Okay, so that's the screen, the game screen. So you will see, you see that we will have cards to swipe left, right, like in Tinder. You know, when you see the face, and then you can choose date, yes or no. And we have three robots. Okay, these three robots are your ministers. So the minister for popularity, the minister for finance, and the minister for ecology. So the purpose of the game is to make decision yes or no, and to adapt or not some measures that is proposed by the cards. You see that these robots have a dark gray. Okay, so a dark gray band like bar. Okay, so this is their level. And when you take a decision, you can affect popularity, money, or ecology, but you don't know how a priori. Okay, so you have to discuss. And the purpose of the game is to not to lose all the bar. Otherwise, you are screwed. And okay,
have we got a minister for sport so we don't?
No, you don't. So this is the tutorial. The first question said solar panels could be installed on the roof of private homes. There is a proposal for financial aid, and the ecological benefits will not be immediate. So Fabrice, what will happen? Because we have to say yes.
Of course, I say yes.
No, we have to say yes, but what will happen?
What will happen? Yeah. We will do some economy and energy.
Louder.
Louder. We will do some economic energy economy.
What? Well, we have to. We are giving aids. So we are the government. So we will lose money, right? Because we are giving money to the private.
À qui s'adresse?
À tout le monde. Pourquoi? J'ai pas compris. So the question is, if we say yes, what will happen to the popularity? Will go up or will go down? Will go up because we're giving aid. Money, we are giving money, so we are going down. Ecology? Up at long term. But first we have to extract first. Okay. So down and then up. Okay, so that was okay. So here we have to say yes, and that's what happens. So we lose money because we are giving to the private. We lose ecology, but then we know at a certain point we will get it back, and we gain on popularity. Sorry, you don't see here; it's popularity. Okay. So,
yeah, good job, Josh.
Okay, so the idea is that every card that we swap, we move forward one season. Right? So here we start in 2050 and we will move forward one season. Every season there is the model that computes possibilities of how many extreme events we have for that season. That depends on the CO2 concentration that we can monitor here. So we are at 600 parts per million, and we have to do better than the RCP 4.5 scenario. Okay, so is it clear? Then now you have to interact and to make the decision. So you are the Minister of Money. You already don't have money. Good. So the transport advisor, that is Greta, propose a subsidy to convert gasoline cars to electric cars.
Who's still driving petrol cars in 2050? I say we just kill them. Any subsidy, they don't deserve money.
So the answer is no.
Well, from the finance minister, absolutely not. No.
Yeah.
Hang on, but you know, electric cars are really going to help us reach those net zero goals. And
we're not necessarily. We're not net zero.
Loud.
We're not net zero. Yeah. Why are they still driving petrol cars? How many people are still driving petrol cars in 2050? Morons.
technology should be very great, so I say yes.
Yes, and then Marie-Dominique is the prime minister, so she decides.
So yes.
So what's your argument? Sorry?
It's only morons that are driving petrol cars in 2050 still, and we shouldn't be giving them any money. We should just we should just ban petrol cars.
So you want to ban petrol cars and have
Yeah, but I guess there's no option to just ban them.
Do you want to slump the economy with no?
So people cannot wait. We need a decision.
Yes.
Come on.
Yes.
Be fast.
Okay, so we lose money and we get popularity up. So now it's the account for the extreme events that happen in the region. So we had one drought. Okay, so this we cannot say yes or no. It falls on us. So it's okay and okay, right? Okay, so we say okay when there is an extreme event, we lose popularity because it's always your fault, even if
Yeah, sure.
then we lose money because you have to pay. There are damages, and ecology, of course, because we have disruption of natural ecosystem. So remember, we had installed the solar panel, so now the panels are operational, and so this is a green card that is the delayed effect of the previous decisions that we have taken, and then we go up in ecology. So that's what they say. There are 3 types of card: blue header, you have to make a decision; green header, delayed effect of a previous action; brown header, notification of extreme events affecting your region. Okay. Okay. Each blue card advances you by 1 season. The ecology gauge determines your CO2 rate in parts per million. The tabs in the top menu give you important information about the game. So we just start. We'll see. Okay. So next question. Do you want to make it compulsory for shops and large retailers to turn off all their lights at night? Yes, please say yes.
Of course. It saves money, right?
No, I want to see the Eiffel Tower at night.
Okay, so I will propose here that we call for a referendum. Okay? So please raise your hands if you want to shut off the light, turn off the lights at night. Well, the large majority say yes, so we do. You are right. Yeah, so yes. So we gain money because we save money also if we, and then we gain ecology, and then the people are not so unhappy because no one sees at night.
Why do you gain money from that, from making the shops turn off their lights at night?
Well, because it's public.
Oh, it's all money, not the government money?
They are the government.
So back this time we got 0 drought. So when we have 0 extreme events, we gain back resources. So there is a notification here now. It's to see that we are doing quite well. We are already saving 0.3 ppm of CO2 with respect to RCP 4.5 scenarios with our action. So good.
Yay! It's so easy. See, why don't we do it?
So you can see that we have all the missions. If you want to play several times, there are many missions that you can play to complete the game. And there is, of course, since it's a game that we developed in France, there is a famous guillotine. I introduced. Okay, so now we finalement la guillotine. The subside for electric cars allow reduction in CO2 emissions. I don't know where there is a train, but whatever. Okay, do you want to issue an ordinance to restrict the use of public water for non-essential usage, such as landscaping, washing cars, filling swimming pools, etc.?
We let them wash electric cars, aren't they?
Now washing electric cars.
Of course.
Well, I think
yes.
I think it'd be unpopular if people can't wash their cars.
It's unpopular.
We've been hit by a drought. We don't want any more drought.
Popular with men. I don't care about the dirty car.
We have swimming pool, yes.
It's underfilled.
Marie-Dominique say yes, so yes, okay. Oh, we are playing. I remind you that we are playing in 2050, and we have not respected the Paris Agreement, so we get 9 heat waves in Africa, and you see that of course we go down. An association for organic and local products asked us to propose local and vegetarian dishes in company canteens. Yes.
Unpopular for the people that like me.
Yeah, I don't think we should do it because our popularity will go down.
It's no low impact.
Still, yeah, we do it.
It's pretty low impact, and you're doing okay right now.
Oh, that's my MATLAB. Yes? Okay, I hear yes. So you see here that we have the impact level low because there is a measure of the impact level of the car, although you don't know if the car is changing things in one or the other direction. The important thing is that you understand that some cars are not, some action is good for advertising, again, pyramid, but is not good for actually being effective against climate change. So this, when you play with school, you learn that the cards that are related to energy choices are the most impactful ones. Okay, so yes.
Why not vegan? Why vegetarian?
Well, we can put more cards. So we are in fall. We have only one flood, so not too bad. And here there is another notification. This notification is what is happening outside the room of power, and is basically when you go there. Here you cannot see, but there is an icon of a present. If you listen to the people, you have like a present in one of the indicators. Then you go back. Oh, okay. Do you like Nutella? The Consumer Association proposed to ban palm oil. Some food producer warned that the transition to another product will have an impact on their profits and then on yours also, because they pay less taxes then.
It's up to you. You have no more money.
Get us the money, yeah. Let's churn out the evil palm oil to get that money back up.
So we keep the palm oil and fill the money, or
Our ecology is gonna go down.
No, keep the Nutella.
No, our ecology.
so you want to keep the Nutella? I say no. No, we like Nutella. Okay. Well, the ecology went down.
That was unpopular.
Not surprisingly, we have no gospel anymore.
Online corporation.
They like Nutella.
Do you want to develop and maintain a database to track community exposure to flood risk? Yeah.
Do we have enough money for that?
That sounds by then. The impact level is low.
Long term, that's going to be good.
Marie-Dominique, Prime Minister, enlighten us.
How much is
it? You have to play the game several times. So.
I don't know. What is it?
Yeah, that sounds popular.
I heard a yeah. So just one drought.
Yeah, how much money do we have?
Well, you have.
We played Baeza, we played one group against the other, right?
About chin money.
When we played in Baeza, didn't we play one group against the other? It was a competition.
Ah, yes.
Susanna wants to compete. But this for me was actually to show you the game. So for me it was easier to play this game. But yeah, I mean, the idea of the game is like, so there are two ways to play when you play with school. Now the game is absolutely free for you to play. I will show you the website. The website is in English, French, Spanish, and Italian. And there are two ways of playing the game. One is the way we are doing it, that for classroom works very well, because although there are 4 people here, everyone is participating. And sometimes you can call for referenda, and you can say like what you think. People can say something, okay? Or the other way is like you can divide your classroom or your colleagues, or whoever, the politicians. We also played with the politicians in groups, okay? And in different groups, they will choose different scenarios, region, and then we'll have to report. So what happened, how far did they go, and so on and so forth, okay? So there are these two ways of playing.
What is changing because in the beginning we chose the region, what does that do? Change the natural disaster?
Yeah, it changes the natural disaster. That, by the way, are computer using the GFDL model.
Really?
Yes.
Really?
Yeah. Wow. The simplified version. Anyway, it's just to have some idea, but it can get very bad.
Yeah, I imagine.
In order to cool down cities during heat waves, botanical researchers propose to green urban spaces. Yes?
Yeah, I think
It'll happen naturally when people die in the heat wave. It's a waste money on this. Yeah, I think it's a yes. Oh, wow.
It's a yes. Then we pay. So normally, normally, okay. Then you have 7 heat waves. You see here also. Then you can comment.
Too good.
Hazard are the heat waves. When the bar gets at that level, what I usually do is that I say goodbye. You're fired. And then I invite another minute.
Yeah, we're saying that.
Global warming increases rainfall variability. Farmers are asking us to build dams to provide irrigation. Benefits will not be immediate.
No.
I think we should do it.
No, you have enough. You have enough.
No, we should definitely do it.
No. Luckily, we have 0 blood. Also, this number can get very bad, as you know, but not this time. The transport consultant proposed, that is again Greta, proposed to develop freight trains to limit the number of trucks on the roads.
Sounds expensive.
Will not be immediate.
But it's expensive.
And we have a present here. We can see what the people are doing. A famous brand starts collecting used clothing stores. So we get some money out of it. Good. What do we do?
I don't think we can do it, guys. We don't have enough money. Look at how low it is.
Ecologically, it's yes, you should.
Yes, no? I take some discussion.
When do we?
No?
Yes, yes.
I heard Marie-Dominique?
Yeah, I think we should do it.
Yes.
Oh!
0 gold spell. No. So far, so good. You survived 2 years. 2 years. That's more than any average Italian government. Belgian, it's more than any Belgian. So here you have all the missions. So we filled up this one. If you finish all of them,
we should do the guillotine.
Yeah, how do we get to the guillotine?
Guillotine, all popularity.
Oh, okay.
There is the need for developing a stormwater committee that meets regularly to discuss issues and recommend projects. This is a very French card. Like, let's make a committee for a committee.
That sounds cheap. I say yeah.
I would say it's a low impact level.
No.
What do you think?
Yeah, but they're going to recommend a bunch of projects.
Depending on the money we have.
Hey, we have no more money.
We better use it on a high impact.
Emily is going to be fired soon.
No. One, drought. The development of freight trains allow reduction in CO2 emissions. Good. There is a talk of limiting the intensive fishing of certain endangered species in the ocean. The benefits will not be immediate.
Yes. Yeah.
It's for CO2 or for biodiversity?
I think we should do that.
Yes. This costs the economy.
Yeah, that's going to cost the
You're going to money. What's happened with the government has no money?
Yeah.
That's like every day, you know.
You're already negative.
I think we should. I think we need the money.
Our money?
No.
No.
No. Okay, so
We're back.
just 3 it to And then we have another icon. Here is the lab. This is the lab that explain you something from a scientific point of view. And when you get here, there is a present on this side of the screen that you don't see. If you get this, you get you recover all the bars, which means like politicians, if they listen to scientists, they do better choices. That's the message we wanted to convey. Do you want to adopt a post-disaster recovery ordinance based on a plan to regulate repair activities, like a civil protection plan?
Prevention is better than post-disaster recovery.
I would say if it's a low impact level, I would wait for the next one.
Yeah. No.
No. Low impact. Oh. Low impact.
These 3 floats. Okay.
My popularity.
The Concorde is back. Do you want to go back to the United States in 3 hours instead of 8 or 10?
Yeah, I think we should authorize this.
I feel like that might get us
really
some money,
popular.
guys.
Yeah, I think
what the people say, do you want to fly, do you want to get back the Concorde and fly back in the United States just 3 hours?
No. No.
Will it bring money back? I think you don't know, maybe.
No, but the impact level high.
Yes.
This hurts.
In terms of what, economy or
climate?
Climate? What?
Well, the climate's doing fine right now.
Yeah, it's doing fine. I think.
Yeah. 600 ppm.
But like, we're running out of paint.
No, you don't want to authorize, no.
You gotta modify that baseline.
Yes.
Black.
It would help the economy.
So, yes or no?
And I think people would be happy though. They would be like, yes, I can finally.
Yeah, I think it would be popular. Yeah.
But you're already popular.
So, okay,
No, no.
referendum. Who wants to authorize the Concorde? Raise your hand. You want to authorize the Concorde? Then it's a no. It's a no. And we lost popularity. We have here a documentary film on ecology was a big hit in cinemas. Good. So we recover some money. Liverpool spell. Do you want to upgrade existing water distribution system to eliminate cracks and leaks?
Does sound expensive.
For sure.
No.
It's a good idea.
Yes, of course.
Yes or no?
Might be popular.
Yes, I heard a yes. Yes. A bit expensive. One drought. An increase in the price of the heavy goods vehicle vignette could make it possible to make ecological investment in the future.
Yeah. Do that. Josh, you're gonna take a hit though.
We need some
Yeah, we need some money and
This is raising
you got enough
taxes,
pockets.
so I'm going down. You should do it.
Yeah, do it.
I think you are.
Now we're on the same number.
The guillotine is coming. Do you want to? Okay, so we can go here. The melting of permafrost releases 30,000-year-old viruses into the atmosphere. This is popular.
Why is it popular?
We want to encourage the use of permeable driveways and surface to reduce runoff and increase groundwater recharge.
Encourage or pay for? Because that's like, I think we should encourage that.
Yeah,
me too.
But not do it.
It's expensive.
Yes.
I think, yeah, let's
It's
do
a
it.
bit expensive.
Yes, it will be expensive.
Is there any way to get money back? Is it possible?
Prime Minister. Yes.
Oh, how did that cost?
Zero floats.
Disaster.
More trees to be preserved and planted in landscape to reduce the amount of stormwater runoff.
Yeah, that's quite cheap.
Yes.
everyone likes trees.
I would, yeah.
How does that cost money? Oh.
Good. Good accident, you are in.
We
Can someone read a meeting?
This costs money, I guess.
Yeah.
It is expensive. Colleges.
But I think we should do
So the education advisor proposed interdisciplinary training in environmental science for science.
I think we have enough money in the budget.
And
We can.
And
Yes.
thinking about her job.
So yeah, let's do that one.
Yes. There have been just one drought. Okay, the transport advisor proposed to reintroduce night train as an alternative to air travel.
Yes.
Yeah, of course.
Yes.
Yes.
Oh my God. Well.
Wow. Was it like ever not hot?
Oh my God, guys. No. Nobody would like to install
Yes.
that.
Yes.
No.
Yes.
No.
Wait, let's go see what the people scandal breaks out. We will be in a permissive flight zone, but we gain ecology, yes, of course.
No.
Would you like to install a 5G network through the country?
No money.
Yes.
No.
Marie-Dominique saying no, and with this I think we can... Oh!
No, wait, guys, we're out of money. We're out
I
of
think
money.
popularity.
Popularity is a
Climate saying raise awareness of climate change in the population. Good. A startup would like to launch space tourism with flights in orbit around the Earth.
Oh, Josh, your popularity.
Yeah, your popularity.
Yes or no?
No.
Money and popularity.
Would that give us money and
I think it will give you
popularity? And popularity.
Okay, do it
We kind
then.
of need it. We kind
Do
of need
it.
it.
Yeah.
Yeah, go yeah.
Two of them are afraid of losing their
Yeah,
job.
do it.
I'm so excited.
Yeah, ecology is doing really well. Yeah, do it. Come on.
Do it.
Yes.
Do it. Do it.
Yeah. Okay.
No.
Yeah. Oh my God, and more.
Okay, here we have this. A transnational fight against rising prices underway. Okay. And then we have the card.
So
Would you like
Yes.
to encourage the use of public
Yes.
transport by
Yeah,
reducing
definitely.
the price of the
If
tickets?
people are mad about
Yeah,
the
definitely.
And then you have some information about mobility and CO2 emissions, but we can take.
Yes.
Yes?
Yes. Okay, all right, that's okay.
Now you're in trouble. Do you want to establish a grazing policy or permitting program to prevent overgrazing?
Is that expensive? I'm pretty neutral on this.
Not very popular.
Not popular. Yeah, our ecology is like high.
It's easy for me.
Marie-Dominique.
I don't know. Tout le monde est dans ton camp, du coup.
I don't know what you think.
Yes.
Yes.
Fabrice say yes. Yes. Oh my God! You see that we are at
11 heat waves.
607 ppm. So it's quite a lot, and we have 11 heat waves.
Oh, that's close.
Solar panels, again, there is a second wave of solar panels, but this time you can decide to install it.
No.
No? With
No.
which money, I think?
Yeah, so we have to say no.
But you're popular.
No.
Wait, hang on.
I'm having popularity.
Oh, no! You have been guillotined.
I've been guillotined.
Oh, he didn't even have a choice.
Okay, so and then plus for floods.
We're out of money too.
Okay,
Oh,
so
this
that's
is-
game over.
Game over.
Your popularity's indicator has dropped to 0. The CO2 total is 608 ppm. You have achieved a minus 5.8 ppm of CO2 difference compared to the IPCC intermediate scenarios forecast. You have reached the winter 2050 25. Congratulations! No, it was good. Okay, so that's it. That's Climarisk. So if you want to play, you can just go on climarisk.ipsl.fr. And this game is free for you to use, download on the App Store, on the Google Store, and to play with your students, with your whoever you want.
Totally doing this.
Yeah. So be the ambassador and enjoy your evening.
Now I understand the government.
Yeah, that's how fun. Because the easier is to make, right?
We made so many good decisions.
Yes.
From our last
We are about her.
Yeah.
Paris.
The precipitation. What I had in mind. We did.